Good morning, everyone. I welcome you all back to the fourth day of the Frontiers of Graph Algorithms workshop. I have the pleasure of introducing the first speaker for today, Professor Dhanupan Nanonkai, who is the scientific director at MPI Informatics. Professor Dhanupan did his ACO PhD at Georgia Tech and then received a docent from KTH Sweden. He has contributed to advances in many fundamental graph problems, including the near linear time negative weight algorithm for shortest path with negative weights, which also won the best paper award at Fox 22. He has also worked on many different settings like the distributed and dynamic algorithms, and is now championing a unified cross paradigm approach, which is what he'll be also talking about today. So without much further ado, I'd like to hand it over to Professor Dhanupan.
Thank you, Aditya, for the introduction. Everyone can hear me? I think it's on, right? People in the back, can you hear through the mic, right? Yes, perfect. Okay, so yes, I will talk about cross-paradigm graph algorithms, which I mentioned a little bit in this panel discussion yesterday. I usually prepare more than what I can finish, so please feel free to ask me questions anytime. I like discussions. Okay, so let me start with notation. I will use this all the time. So n is the number of nodes in the graph, m is number of edges, and this tilde O notation has some polylog factor. Okay, polylog n usually. Okay, I already talked about this yesterday, so let me just redefine the model once more without saying too much about the problem. So yesterday I mentioned this open problem, reachability, where you have a graph, but you cannot read it directly, right? You can access it through cut query, where you can ask about, you can ask about the set S, and then you will be told the number of edges going out from S, right? And the question that I asked yesterday was, how many cut query can you make to be able to answer whether there's a directed path from S to T for some particular vertex, S and T, okay? We know n square and we don't know anything better, and that would be my favorite problem, that to break n square, like n to the 1.99. Okay, so now we know at least one model that is not sequential model, right? We probably know more. So let me get back to sequential model a little bit. And in our textbook, when we learn algorithm like minimum spanning tree, reachability, and min cut, and so on, we usually look at this runtime, right? Sequential setting, where we like to see how things work. Like we have prim algorithm that works pretty well, you know, how to use breadth first search. And if you go a little bit advanced, you might have seen Carter's algorithm. There's more than one, by the way. But you know, there is not just that, right? Nowadays, there are more. There are these cut queries that I have talked about. There are some other settings, streaming, parallel algorithm, distributed algorithm, and you can imagine there are more. Quantum, maybe some learning augmented, and so on. So let me give you some example again, so you have the runtime is unlimited, okay? And I can also define something a bit more complicated called dynamic stream, where I can add edge and then delete edge later as well. So sometimes people unfriend each other, and you record this somewhere, right? And the graph now changed, okay? The edge is not in the graph anymore. So you can imagine there are many variations of this. Okay, so and what happened? So over the past few decades, we have new algorithm for, you know, each problem and each model, right? We can invent, and we still have to do that nowadays. I will show you later that there are still a lot of open problems for this direction, right? But today, my goal is to discuss with you the possibility of cross-paradigm algorithms, or as I mentioned yesterday, some people call it universal algorithm. model independent algorithm, model agnostic. And I'm not the only one who works on this. I think there are a lot of people, and that's why there are many names. I just think this is a good thing that we have more. So I hope there are more people joining force to work on this topic. So what do I mean by that? So at least this is how I interpret this. Maybe other people have different interpretation. I would like that for every algorithm, for every problem, we only have maybe one algorithm. That would be the ideal case for me. Think of it as like uh, uh, each problem is a task that you have to do. Maybe you have to put something together to get a chair. You have to put something together to get a drawer. I don't know, a cabinet or something else, right? And the algorithm should be a manual how you do it. And now your task is to make that happen. But now, in different models, you have different tools to do it. So different models have different limitation and different power. So it provides you different tools. And so you want to use these tools and these manual to solve the problem that you want. Okay? So I want to decompose this, I want to have just one algorithm that allows you to use different tools from different settings to solve the problem in different notion of efficiency. That's the hope. And I guess maybe by now you might ask, is it too good to be true? Is it just a dream? Okay, I'm not sure yet, right? And this talk, at least I will at least try to give you some example of something that we know already is still small amount of evidence compared to what we have in the world, but hopefully it gives some hope. And also, I would like to say that we should try this direction anyway, even though it might not exist in the end. And the reason is that so far I think it's a nice approach to understand the problem. To me, having a new model is an opportunity to understand the problem better. It's provide a new lens, a new way of thinking. And we sometimes we have new tools from the model, and these tools might be useful elsewhere as well. So I will try to give you some example now. But any questions so far? So if not, then let me start with kind of a textbook or almost textbook example. Minimum spanning tree. So you have learned Kruskal, you have learned Prims. Can you raise your hand if you have learned Barufka? Yes, so most of you also know it, right? So to me, I think Barufka is something that we should learn. Like we should start with Barufka, and the reason is that it kind of works in many settings. So let me remind you briefly what Barufka is, right? And I think of this as like a manual for MST. So you just repeat until one node left the following process. First, for every node, right, you find the minimum weight h incident to v. So for example, here this is my graph in the top. Sorry, I'm not sure if you can see the red point. The top picture is my graph, and now the vertex A, for example, pick this edge because it's the minimum between the two. Right? And every edge picks that, you get these green edges on the second picture. And now you contract all these edges together, meaning that now you want to draw this circle along these green edges. So this is one circle here, and then this is one circle here. Forget about this green, it's not there right now. Right? So now you kind of think of this as one big node, and this is another big node. So now you have two nodes. Okay? So this is called contraction. Now you only have two nodes left, and then you repeat the process. And you get this edge, number 10, over here. And now you only have one vertex, and then it's over. Okay? So, okay. Okay, what if all the edges are disjoint? Meaning that maybe you get a cycle. Is that what you mean? Right?
Like we selected the minimum weighted edge.
Yes.
What if for each vertex it is different?
For every vertex, it has different edge, right? Okay, now that's one caveat. I would assume for now that the minimum is like one thing you can assume that the weights are all different, for example, right? Then that's not going to happen. I can guarantee you that, right? Or the other way you can do it is there's some consistent way that you break tie. And so again, that would not happen. Yeah, because that would introduce a loop and that would be a little bit of a problem. But we can avoid that. Any other question? Yes, so that's pretty much the algorithm, and you can now, I hope you are convinced that you will get a tree at the end, at the least. And the claim is that that is a minimum spanning tree. Okay? I hope it's simple enough. So now what happened? Another claim is that these only need log n steps, repetition, because every time you reduce the number of vertices by half, because two vertices should be combined, one vertex should be combined with some other vertex, right? And these can be implemented in quite a few settings. So in dynamic string setting that I have shown you before, or even stream, right? You can imagine that you only need roughly n space to remember these green edges in each graph of this algorithm. And once you have that, you can kind of memorize how the contraction happened. And then you can make another path to find some new set of edges. And since you only need log n repetitions, you only need log n reads through the stream. Okay, so that's one example. And since the algorithm also works in the PRAM setting, for example, for a similar reason. And I'm not sure you have seen this in the quantum setting. It turns out that it can be done as well. And the only tools that you need is something called quantum multi-mean finding, which roughly says that if you have a lot of numbers, okay, if let's say you partition the numbers, let's say we have m numbers. Think of m as the edges, right? The number is just the weights of the edges. And you partition these n numbers into groups. Each group is of to n groups, sorry. You have n groups of numbers. You can imagine that you partition the numbers by, if 4 and 7 incident to A, then that is one group, right? And then 4, 9, 15, 6 is incident to D. That's another group, okay? And for each group, you want to find the minimum of the group, okay? There's a quantum algorithm that can do that in root mn time. So that's the only tools that you need, and once you know how to do that, then you know how to implement the first step in root mn time in total in the quantum setting. And you just have to repeat this again log n time. And yeah, there are other models that you can also implement this. It somehow, whenever there's a new model, it seems like this algorithm is going to work. I'm not sure if anyone has counterexample. I don't know of. So that's one simple example. Any questions so far? No question? Then let me ask some question. Maybe you might realize that Borufka is actually a bit slower than Prim and Kruskal, right? There's some log n factor. And so maybe this is why we don't teach it as much as Prim and Kruskal, I'm not sure. Yeah, but to me, why I think it makes sense to teach it these days is because I think there are many more other factors that are more important than polylog n. So maybe for now we should not worry about that too much these days. And also, if I understand correctly, there's a MST can be solved in actually linear time, right, with randomized algorithm. And in that, as far as I understand, there's this Borufka somewhere happening in that algorithm too. So it's actually play a role in the fastest algorithm we know of.
So actually, I think that the reason we don't teach Borufkas is because students are not used to edge contractions.
But edge contraction, maybe, I don't know. Is it that complicated?
It's not.
But that makes sense too. I'm not sure. Yeah.
It's sort of a meta question, like going back to your initial motivation, like what feature do you think Borufka has, whether it's Prince and Kruskal, that allows for such cross paradigm?
Yeah, what feature does Borufka have that allow you to do this? I don't actually have an answer. I think one thing is that it's easy to parallelize. I think one thing that we need from this kind of algorithm is that you don't need kind of many for loops, for example, right? And Prim and Kruska is pretty sequential, I think. That would be one ad hoc answer. Yeah. In the very end, I would try to say a little bit more about not about Borufka, but about like this kind of question in general as well.
I mean, also it's very local in the sense that every vertex is just contracted or original, is just looking at the neighborhood and making a decision.
Yes, your comment was that it's another good reason is that it's local algorithm, right? And yes, as someone who came from distributed algorithm community, I would agree with you that this probably is an important aspect as well. That the algorithm should be local in some sense. Like you don't need to look through the whole graph to find something. Yes.
Is it even a log n factor slower?
Is it even a log n factor slower? So Berufka is m log n, right? Prim and Kruskal is like what? M plus n log n?
That's prim.
That's prim.
Kruskal is whatever it is, m log star.
M log star. Yeah. But I hope the claim is correct that log n factor slower is kind of correct, right?
But also the best deterministic algorithm by Ramachandran and Sethi, that also uses, I think, Borufka in it.
Yes, I asked Petty whether he used Borufka in his deterministic algorithm. He said it was 20 years ago, but he think he used it. Yes. So you confirm, right? Yes, I agree that even the best deterministic algorithm, it is the best. We don't know its running time yet, but it is the best. It used Borufka in that algorithm as well. All right. Any more question, discussion? Okay, now let me, maybe one example is not convincing enough, so let me talk about some other examples. Let me start with this. MST, minimal spanning tree, is about connectivity, right? And there are quite a few extensions of that. One of them is if you put direction on the edge, then you can talk about reachability, for example. For example, ST reachability that I talked about before. Or you can put weights on the edges, and then we can talk about shortest path, right? And maybe we can ask about not just how the graph is connected, but how much the graph is connected. And we talk about minimum cut now, which means how many edges do we have to remove to disconnect the graph into two parts, for example, right? So these are all kind of textbooks problems, right? You probably saw these two in a first few lectures in basic algorithms. And if you study randomized algorithm, again, you probably have seen Carter's algorithm, which takes roughly n squared time. And actually, there's a few follow-up papers on this. So this problem is by now known to be solvable in near linear time. Okay. A question for the audience. Can you guess it? Among all these problems, which problem can be already solved across many models? And that would be my next example. Can you raise your hand if you think it's this one? How about this one? How about this one? Yeah, so most of you guess it, right? Yeah. We learned about this, the last one in our course, but somehow it's the first one that we kind of know more about it. Yeah, so this problem, mean cut, can be solved in dynamic stream in log n passes. In distributed setting, roughly root n rounds, which is kind of a golden number for distributed algorithm people. And in PRAM, parallel setting, again, some linear work and polylogarithmic depth, if you know what it is, which is, I guess, what people would hope for PRAM as well. And yeah, there are other settings too. So this would be the next example. This is a joint work from a few years ago with Chapnik, who is also here. And I think some slides I stole from Sagnik, so thanks a lot. Yeah, okay, let me start by making a quick detour. Some simple puzzle. I hope most of the people here can solve this. Let me call it a hidden matrix problem. So now you have a matrix. Again, you cannot read the matrix. You have to make query instead. Okay? And I have one promise to you to make the problem simpler. The promise is what I call monotonicity, meaning that if I look at every column, the minimum of that column never go up. This is what I mean. This is an example. This is the minimum of this column, and this is the minimum of this column, and so on, right? And you notice that the minimum only goes down or stay on the same row. It never go up. Okay? That's what I promised. And now you can make query to this matrix. The query that you can make is you can just point to one entry and ask me for the number, like value on that entry. That's it, right? And the goal is that we want to find the minimum number in this matrix. The question is, how many queries do you have to make? Any guess? Did I hear n? Do people agree with the number n? Yes. Okay. So if you want to think about it yourself, again, maybe close your ears and maybe sing a short song. Okay, I will now tell the solution. So yeah, n, I think in log n, sometimes I just throw in the log just because I'm not sure, right? I don't care about log too much. But yeah, I think n log n should be fine. The solution is you find the minimum in the middle column. Let's say it's this number. Okay, so you just make inquiries already for this part. And then you know that since the minimum only go down, so it should be either in this region or this region, if not this itself, right? So you make a kind of recursion in this green region. That is step 2 here. And you know that every time you search area kind of half by size, right? So the recursion will not cost you too much queries in total. And so that gives you n log n. Any question? Okay, now let me get back to min cut then. Again, just a reminder, the min cut is the problem that you want to remove edges, maybe the minimum number of edges, the minimum weights, total weights, that split the graph into 2 parts. Okay? How does it connect to this matrix, mean entry? And now I have to start by talking about another Karger algorithm. So Karger that you learn in the textbook takes n squared time. There's another Karger that takes m time, like linear time, roughly. Okay? And one of his key breakthrough idea is the following claim, that you can find spanning tree T that crosses the min cut at most twice. What do I mean by this? Let's say this is my spanning tree, this red thing over here. Okay? Notice that this is my min cut, right? Notice that the edges that the overlap between the min cut and the spanning tree are these 2 edges. Okay? This is what I mean by spanning tree that cross the cut twice. And you just have to believe me that you can find this kind of tree. Okay? The algorithm, if you want to know how it works roughly, it needs 2 steps. First, you have to sample some edges, okay, using some distribution. And then you have to keep finding minimum spanning tree many times, roughly log n times. Okay? And magically, the claim is that one of those trees will be this magic tree that we are looking for. Okay? So we just have log n tree, and one of them will be a good one that we have to do something further. And I claim that this part itself is cross paradigm. Sampling, that's not too bad. You can do it in most settings. And then finding spanning tree, I just show you Borufka algorithm that makes it work, right? So In streaming, for example, you need something called AGM sketch, which is a pretty cool technique that you should learn if you want to learn about streaming. But in any case, this part is fine. You can do it in most settings. People now know how to do it well. But after that, now what do you have? You have kind of this spanning tree. Let's fix one spanning tree now. In the end, there will be more, but let's just fix spanning tree, right? And let's assume that you know that this spanning tree cross the cut only twice, like maybe these two edges, right? Now you can imagine that maybe you can write a matrix that each entry in the matrix corresponds to the value of the cut for some pair of edges that you would guess that it would cross the cut. So now basically your job is like you pick two edges in the tree, right? And then from that you can, again, believe me, that you can quickly compute the value of the cut that correspond to deleting two edges. For example, if you delete these two, then this would be one part of the cut, right? And then this would be split, and then this part would be one big tree which correspond to like one part of the cut again. Okay. So you can question?
Sorry, I guess I missed that. So can you tell me again, how are you filling the entries in the matrix from the street?
So for every two edges, when you assume that they are the two edges that cross the cut, okay, it will define the cut in some unique way, okay, and when you define the cut, then there's some value of the cut corresponding to that, right, and that is going to be your number here. For example, if I cut these two, then this is a cut corresponding to that two edges, and if you sum the number up, I think it would be 10. So you would write 10 here. Okay. Now it looks closer to matrix, right? That we looked at before, and maybe one thing that I can claim is that it is efficient to compute n entries in this matrix. Okay. For example, if you have one stream path, right, then you can probably try to guess n pairs of these vertices, and then you have n numbers, and then you just go through the stream to try to find the cut corresponding to these n pairs, right? And you just have to remember n numbers for that stream. And in other settings, you can do something like that too. So you may hope that, but the part that is inefficient is that you cannot look at all the n square entries, right? That would be too much to ask for. And for example, in Carter's original algorithm, he needs to use some sophisticated data structure, dynamic programming, has some dynamic trees and so on to solve this problem, to find this particular number. And in other model, somehow we don't even know how to do this at some point. So people have to talk about approximation algorithm or assume that the graph is simple instead to get around this problem. So I would say that at least the way Carter did it was not cross paradigm. I don't know how to implement that particular approach using dynamic programming. And by the way, dynamic programming is a basic technique in sequential setting, but it's hard for me to imagine that itself is a technique that can be used elsewhere because it's pretty sequential. You need one step at a time to do something. So we usually need something else. And one hope that we might have is whether this matrix has this monotone property that we had before, right? If it does, then we can do this kind of binary search or divide and conquer to solve the problem with less queries. Unfortunately, that's not the case too. But the good news is you can do a little bit more, and then you can get a matrix with a nice structure. So this is basically the observation is this. If you have this tree and now you kind of decompose it into parts instead. So let's say this tree, we have one part here and one part here. And let's assume again that the two edges that we are looking for is in, one of them is in the first part and the other one is in the second part, okay? Now we write this part as a matrix again. So we have this edge, E1, E2, E3 as a row here, and then E1 prime, E2 prime, E3 prime as a column here. And then again, you can fill in the numbers here using the value of the cut corresponding to cutting some edges like E2 and E2 prime, right? Meaning if you cut these two, then what is the number? Suddenly, this matrix is monotone. Okay, the matrices from tree is not monotone, but the matrices from path is monotone. Question?
Can you please repeat how are you taking the paths? Just linear?
Right. Right now, I did not tell you how I compute the path. Right. Right now, what I claim is just that if you pick any two paths and you write down the matrix, then it will have this monotonicity property. I did not say yet how you can get these paths. Okay. Any question?
So just to understand, we'd have one such matrix for every pair of paths in our decomposition, right?
So-
I mean, we have a decomposition of the tree into paths, and we have one such matrix for every pair of.
Yes. Okay. Okay. Yes. That's going to be my next slide. Yes. But you are answering the question already. Basically, there is some notion of tree decomposition into parts, right? There are actually more than one. So you can use basically any of them and it should work. Okay. I will show that in a moment. But not in much details, unfortunately. But yeah, assume now, okay, first, why you might wonder why this is the case, right? I cannot have a full proof for you today, but you just take a picture of this. This should be enough for you to prove that the matrix has that property. Basically, that matrix, right, it's kind of a combination of a bunch of matrices corresponding to different edges. And the matrix, you can write that matrix as a sum of different, three different things. The matrix that looks like this, where you have the same number on the same row, or you have the same number on the same column, or you have the same number on kind of this box and this box, something like this. Shagnik will be able to tell you more, I hope. I kind of forgot most of this already. But yeah, once you have this, then you can prove that the combination of such matrices will give you this monotone property. And now, yeah, as someone has pointed out here, we can decompose the tree that we have into different parts. One example that we can use is called heavy light decomposition. Do you know what heavy light decomposition is? Okay, it's again a nice technique. Let me just say it briefly what it is. So you start from the root, and then you pick the largest subtree among the two sides, among your subtrees, right? You go there, and then from there you do the same thing. You pick the largest subtree. So you keep going like this. So now you have one part here. That is your first part. Okay? And now maybe you start here, and then you do the same thing. Like now you have a bunch of trees, right, that are not in any part yet. From here you do the same thing. You go to the heaviest subtree, and keep doing that. You get another part. And you do this everywhere, then you get a bunch of parts out of this. And every part is gonna be short. That's one thing, right? And this is called heavy light decomposition. So that's one way you can get, you can decompose the tree into a lot of parts. There's some other way. For example, there's something called bow decomposition. That's a different notion that people use in distributed computing a lot, I think. Yeah, but just believe me that you can do this decomposition. And usually this heavy light, okay. Now it depends on which setting you are using. You might need different decomposition, but in most settings, you can do some version of decomposition. Yes?
So can you define like how are you defining the heaviness here? Like
Heavy just means heavy means more number of vertices. Like if you look at this tree, right? This subtree has more number of vertices. Okay. Um, so I will skip there's one details that I skip. So if you try to mash all the paths together, actually there are too many pairs that you can create, right? There could be like n paths from this decomposition. So you can have n square matrices, which is bad too. So there is some kind of simple rule that say how you can mash the path together so you don't have so many matrices. But I'm gonna skip that part for now. You actually gonna see from this rule. This is pretty much the rule, but I'm not gonna explain it here. Okay, you just have to define some notion of degree and then you match the path if the degree is large enough between them. Like there's a lot of edges between them basically. Okay, and then in the end, the algorithm, this kind of sketchy algorithm is you just have these three steps. You have this tree, which is computed from Carter's algorithm, and then you have to decompose it in some way into parts. And then you match the parts together using some rule. And then for each pair of parts, you have a matrix. So you simulate this matrix entry algorithm that we have seen in the beginning. And that's it. And for example, if you want to simulate this in the streaming algorithm, the first part, you can just use once you have a tree, you can just decompose the part without reading the stream anymore, right? So you can just use internal memory to compute it. And then the second part, you can use something called cut sparsifier, or you can use another algorithm called Mishra-Gries. And the third part, you just simulate this algorithm that I mentioned before, and you have for n pairs at a time. Like you need to know the whole column, right? And for that, you just read the stream once to get the value of the whole column. So it's a little bit sketchy algorithm, but I hope you get an idea how Carter's algorithm works and how you might modify it to work in other settings. So my conclusion for this is that there is one framework that gives tight bounds across the model for min-cut right now. It turns out that it's not only for other models that you can use this idea to solve the problem better, but okay, we did not think about this at all. I think until the very end when we get pretty much many results that we start asking ourselves, can we also do it in the running time setting, that's classical setting, right? And it turns out that you can check log factor from Carter's algorithm using this second step as well. So now, this is what I like about thinking about different models. Sometimes it helps you to improve the the algorithm in the classic model as well. Yes, that's a conclusion. Now we have minimum spanning tree connectivity, min cut at the least that works across many models. These days there are many other examples done by many other people. Some of them are in this audience. Let me just highlight one of them for now. So a few years ago, I was obsessed with this negative weight shortest path problem. And we have this reduction which show that you can reduce in the sequential setting from negative weight shortest path, meaning that you want to find shortest path, but the edge weights could be negative, right? You can reduce it to non-negative setting. So once you have that reduction, you can just use Dijkstra algorithm, for example, to solve the problem. It turns out that that reduction works in many other settings as well. Parallel distributed quantum, for example. And the hard part is actually how to solve the problem in the non-negative case. For many other settings, we don't know how to do that. And that would be one of my open problems for you. But it turns out that recently, just a month ago, Glenn Kuiper and my student Yonggang Jian and Tashkun Saranurak, who is here, and also Jason Lee, post a paper that shows that you can actually, I should say that my algorithm is randomized. So now they show that the algorithm can be deterministic. And according to my student Yonggang, maybe Tashkun can correct me if you disagree with Yonggang. But Yonggang said that this framework rely a lot on this algorithm that we developed that works across different settings. So again, that's how I like this kind of line of work. So string algorithm. I know pretty much almost nothing about this area, but Tomak, who is a postdoc, a group leader in my group, is an expert in this area, and he claims that he also used this approach to understand string algorithms. So he made many, I guess, progress already in the classic setting, but he also studied compressed string. When you know, like string has a kind of had a zip, right? You compress the string, and then you want to do something with the string in this zip form without decompressing it. Or in communication setting and dynamic setting, when the string gets changed as well. My question to the audience here is also, if you are expert in other area, is this happening? Maybe in computational geometry, Arindram, any thought? Right? If you have any thought about other areas, if you know of other example, please let me know. Maybe let me mention one open problem. One of my favorite problems right now is how to solve max flow in N communication. I will get back a bit to this later. So all that said, right, it seems like there are a growing number of examples, but I feel like we are still very far from this kind of dream goal. And so this is my best attempt to explain to you, in different setting, different problem, what happened, and you can see a lot of question mark, which means that there's a lot that we don't know. And I want to point to a few problems that I would be super excited to know about with this exclamation mark. So for max flow right now in the communication setting, we can get n to the 1.5 communication. If you don't know what it is, wait for next slide. In the combinatorial setting, meaning that if we are not allowed to use continuous optimization, then even n to the 1.5 is not known. And for non-bipartite matching, I guess we know almost nothing. So I should put exclamation mark everywhere actually. I would be excited to know about this in all the settings. So a disclaimer: this might contain some error. If you found it, please let me know. Let me pick one problem to talk a bit more, which I think is a bit doable. So maybe some young folks here might be able to bring some new perspectives to solve this problem. It's a communication complexity of max flow in unweighted undirected graph, and I want it to be combinatorial. So what is the problem? Now you have a graph as usual. You have input, unweighted, undirected. I partition edges into two players. At least got some of edges here. Bob gets the rest. Okay? And now Alice and Bob have to talk to each other to compute the max flow or to compute the mean cut, let's say the value of the mean cut in this graph. Is the problem clear? And the question is, how many bits of communication should they talk to each other? Okay. So if we use, this was known by the expert for many years already, but it was written down recently in these two papers that you can solve this problem in n to the 1.5 communication, even for the harder problem of that is called mean cost flow on weighted directed graph. Okay, so with this fancy tool, you can do a lot. But if we want to do something combinatorial, meaning that you're not allowed to just manipulate the numbers and then send these numbers around without understand. At least to me, I don't understand what these numbers usually mean, right? If you want to do something similar to what we learned in the textbook about mean cut, then right now we know how to do this in n to the 11/7 communication. And the goal that we want is to improve this from 11 to 10.5. If you get this, then you get n to the 1.5, which is going to match this number over here with combinatorial algorithm. So I don't know, maybe 0.5 is probably not too far to do. And if any of you have ideas, please let me know. So that kind of conclude my second part. Is there any questions about this second part of the talk?
The cut version is that steady, like instead of the same undirected like unit weight graph, but edges are partitioned and you want to understand the thing.
So in this which setting again?
The communication, the last slide. The edge set is partitioned and you just want to like jointly figure out the min cut. I mean, if you do the max flow, it's fine, but are they like even communication wise are they equivalent or?
You mean you talk about the min cut, like global min cut? Is that what you
Yes,
mean?
yes, yes.
And the question is whether it's equivalent to max flow?
I mean, you can take all pairs and like,
Right.
yeah, but
So, min cut can be solved by max flow. The classic textbook algorithm is all pairs max flow, right? But Debmoya and many other people came up with this technique that allow you to just solve log and max flow. So yes, that technique I think is again cross paradigm. So it works in this setting and in most setting as well. So once you solve max flow, then you're gonna solve global min cut as well in most settings. I hope that answers your question. Any other question? Okay, so I will just spend remaining almost 10 minutes. I hope that I have that to discuss the question that was raised a little bit before, why cross algorithm, paradigm algorithm might exist for some problems. So maybe there's some feature of the algorithm, but that part I'm not completely sure yet what the feature, right? So what I want to discuss today is maybe because this algorithm that we think is cross paradigm, it kind of works in some weaker model of computation. What I mean by that? So maybe this is even a more dream, and maybe it's even harder to achieve or not harder to be true. Is it possible that we actually have one model that I would call universal model, right? That allow you to only use some very simple tool, which means that you can simulate this model in many other models of computation. And at the same time, the model is strong enough that you can implement all these manuals for the problem in this universal model. Okay. Again, that sounds too hard to be very quite probably impossible, right? So let me mention some of them, some of the attempts that at least I think it might be a candidate, but I'm not very sure yet. So right now, this is the previous picture was a dream. This is more like reality. So we have something called dynamic query that I will discuss shortly that can be simulated in some of these models, and we can at least simulate some of the known algorithm in this dynamic query setting. There's another model that came out from distributed computing called minor aggregation that also works in some of these models. And in the string algorithms, Tomak again told me that there's a model called pillar algorithm that kind of works in some of that he used to explain why some algorithm works in many models. And maybe there are more that I'm not aware of, that if you can let me know. So I think I only have time for just one model, so I just talk about this dynamic query a little bit. Again, I'm not sure it's the right model in the end, right? I just want to give you a flavor of how I think about possible models that might work. So let's try. We know some cut query algorithm by now, right? So let's try to simulate them. And if you try to do this, the problem that you will run into immediately is that it's inefficient even to specify all the queries, because if you want to specify the cut, right, you have to point to n vertices to specify the set that you want to define the cut. So if you want to do that for n times, then it's already n square running time in the traditional setting. So that is too much. Right? For example, if you want to make this cut, then you need the time S1, the size of S1, the size of S2, and so on. And usually we will need at least n cut queries, so that would be too much. Yeah, this is what I just said, right? You need n square time. So the proposal of dynamic cut query is that let's change the constraint a bit. You cannot specify any cut, but you can specify the cut Si by adding or deleting nodes in one of the previous cut that you have, S1 to Si minus 1. For example, you can define S1 to be maybe A and B, and here you pay the cost of 2 because you have to specify two vertices already. And then you define S2 to be S1 union C. So S1 is this, then S2 is bigger, right? Now you can specify bigger cut by just paying one, the cost of 1. And then you can specify S3 by saying that it's S1 minus A. So it looks like that. Oh, sorry, minus A and C, that's it. Oh, yeah, it's correct, yeah. Question?
Why not allow union of, let's say, S4 is union of S1 and S2?
I think it makes sense to allow union. We don't allow it right now because at least in our attempt to explain what happened, we don't need it, and it might be hard to implement that cut query in some settings. Yes, but it's a good idea actually to allow that too. So I want to mention that this is not only the problem in cut query setting. If you know anything about metroid and submodular function, right, you have to make this kind of query too. Yesterday you probably see a little bit about submodular, I guess. Like you specify the set and you ask for the value of the set, right? In metroid intersection problem or metroid, you have to do the same thing. You have to specify the set and ask for the rank, for example. And so this kind of idea came out from our paper a few years ago, that we actually want to look at metroid intersection problem, which encapsulate a bunch of a bunch of graph problems and other problems. And what happened in the past was that people have a good metroid intersection algorithm, and it has these special cases, so they have to spend one paper, for example, here to solve one problem, and then they need another paper to solve another problem. Simulate the same metroid intersection algorithm, but now for different problems, you have to do different things. And in that paper, we kind of show that you can just, the existing metroid algorithm, metroid intersection algorithm, actually can be described in the dynamic metroid query setting. And once you do that, you can use dynamic graph algorithm, which we know a lot about these days, to translate them into sequential setting for all the problem at once. And that is the idea that hopefully maybe work for cut query and other kind of query too. I saw maybe some of you have question.
All of these bounds on the left are for the number of queries in the
Sorry. This now running time. Now I'm talking about running time. So there is some upper bound on the queries for metroid intersection, and then when you try to translate into running time, then you need to look at this algorithm and then say how it works for this particular problem. That was how it works before. Any
What is that cross? The red cross?
cross mean okay, yes, thank you. So check mean that it kind of matched the previous word. So basically you can just now look at this dynamic metroid intersection problem algorithm, right? And then just translate the algorithm automatically, and you get the same bound as the previous word. Cross means that you don't match the previous word. And the reason is that, for example, this is for something called pseudo forest, but it relies on Maxwell algorithm. And Maxwell has nothing to do with metroid intersection right now. So this algorithm relies on some other tool, and at least right now, the tool through metro intersection doesn't really match the way you can achieve through that tool. Yeah, so there are some problems that we don't know how to do, achieve the best result we know of right now. Any other question? Okay, so then my claim is this. Now I'm getting back to cut query. So I talk about reachability a lot, right? One reason that I like reachability is its connection to a problem called submodular function minimization. But the other reason is that maybe it can help us understand reachability in many settings at the same time. So let's make a conjecture that reachability can solve in n dynamic cut queries. That's already a lot to ask for. We don't know anything better than n squared. But let's assume even further that you don't need many routes. Just like global min cut, right? You make a lot of queries at the same time. So the number of routes is not much. If you can do that, then I claim that you can get new bounds and it's going to be optimal up to polylog n for a bunch of settings. Distributed congest, dynamic stream, congested clique, and if you have some extra constraint, then it's going to work in parallel setting as well. So that is one dream. It's still a dream. One reality that at least we have is that for min cut that I have explained to you the algorithm, that can already be explained in dynamic cut query setting. This is a work by Shaknik and his students. So that algorithm itself, I think with some more clever ideas, you can implement it in ON dynamic cut query and with good parallelization. And with that, so you can get this efficient algorithm in congested clique, dynamic stream, and parallel algorithm at the same time. So I don't think I have time for the rest of this of the talk, so I will just skip to conclusion. Yeah, so I'm trying to advocate for this thinking about cross paradigm algorithm, right? And I think we have a growing number of examples, and even though it's not going to be true, something that we can realize in the end, I think it's a good way to approach the problem to understand it more. A dream is whether we have this universal model that can explain what we can do for a bunch of settings. And maybe for now, the barrier, already a big dream is whether you can solve max flow in these much cut queries, even dynamic cut query. Maybe a smaller problem, but still hard, are these two problems. Max flow in ON communication or reachability in ON cut queries that I have explained already. And there are many other problems that we don't know in most settings. And I guess if you want to pick one problem and try to solve it, it would be already great. Non-bipartite matching is one of them, right? That we don't know even in the sequential setting what is the base running time. Metro intersection, and even shortest path in just unweighted undirected graph. We don't know that. We know that how to solve that in sequential setting, but mostly in other settings we don't know how to solve this problem. Yeah, thank you so much. And you have any other questions?
So one question, so are there any problems for which we suspect that this kind of a cross paradigm
Can we all settle down a little quickly, please? Right, so welcome back everyone. The speaker for our next session is Professor Debbalya Panigrahi, who is a professor of computer science at Duke University. Professor Debbalya did his PhD at MIT, and before that he was a master student right here at IISc. He primarily works on graph algorithms and algorithms under uncertainty, and he has made some seminal contributions to the field, like the subcubic all pairs max flow computation algorithm. His research excellence has been recognized with many awards, like the NSF Career Award, amongst others. Please join me in welcoming Professor Debbalya to the stage.
I think it's on.
It's on.
Okay, not yet.
It's on now.
All right, so thanks very much for the introduction. Thanks to the organizers for organizing this workshop and for having me here. As it was mentioned during the introduction, I was a student here 20 years ago, and this is where I learned sort of my first, I took my first baby steps in learning algorithms, including from people in the audience like Kavita. So it's always a pleasure to be back here. All right, so what I'm going to talk about today is a class of problems called network unreliability. And as has been the established tradition from yesterday, let me talk about my PhD student, Roshu Chen, who is currently on the postdoc job market. So, you know, if you have positions for him. Some parts of this work are also with William Hay, who was my undergraduate student at Duke and is currently at CMU as a PhD student. And with Jason Lee, who was a postdoc at the Science Institute when most of this work happened and is now a faculty member at CMU. All right, so what are we talking about? At a very high level, the question we want to address is how robust is a network to edge failures? Now, of course, this question makes sense in a lot of different contexts, and it's sort of cross-paradigm in the sense that it doesn't matter what application domain the network represents. So whether it's a circuit or it's a transportation network or a telecommunication network or something else, the purpose of networks is to connect. So you would like to understand how robust these connections are. Sorry?
Robust airlines.
Yeah, so as we have seen in the last few days, certain connections may not be so robust. In this talk, I'm only going to be talking about undirected graphs. Many of these questions also make sense for directed graphs, but I'm not going to touch on directed graphs in this talk, primarily because I can't say anything interesting about directed graphs. I don't know the answer to any interesting question. But let me define these two terms, robust and edge failures, a bit more precisely. So there's only one notion of robustness I'll consider in this talk, which is whether all the vertices in the graph remain connected. Okay, so a robust graph in my language is one where the graph is connected, and a non-robust one is one that's not connected. And the type of edge failures that one might be interested in, there can be an entire range that one considers. Maybe the most popular ones are sort of worst case edge failures. So you can ask for the smallest number of edges whose failure disconnects the graph. And that's indeed a problem that we are all familiar with. That's the minimum cut problem. But in this talk, I'm not going to have this worst case lens. Instead, I'm going to try to understand what happens to a graph when edges fail randomly. Okay, so that's the sort of that's how I'll deviate from the standard min-cut literature in this talk. All right, so why do we care about random edge failures? There can be many answers to this. One answer could be that maybe in certain settings it's a better model for the real world. in let's say one of these types of networks that I showed here, it might be more reasonable to say that there's the failure of individual links is a random event rather than someone actually coming in and trying to create problems for you. And in fact, there are a lot of books that are written on this. So this topic of network reliability is a popular topic. Most of these books talk about various empirical methods that you can improve the reliability of a network. In terms of this talk, and to some extent my interest is because we can say very little about what happens to a network when there are random failures. So this, to me, that's where my interest comes from. Algorithmically, our understanding of random failures in a network is kind of poor. Okay, so with that, let me now formally introduce my problem. So I have some undirected graph. I'll always denote the number of vertices in the graph by n and the number of edges in the graph by m. Every edge in this graph, I'll assume, fails independently with an identical probability p. So there's a sequence of IIT events that happen on all the edges. Either the edge survives or it fails. And whatever comes out of this random process, I'll denote that by g of p. Of course, this is a random graph, but that's the notation I'll use. Now, I should make a couple of comments. Firstly, independence is crucial for everything that I talk about. Of course, you can imagine that in many settings, independence is not true. There's some dependence between how various edges fail. But in this talk, I'll assume independence throughout. The fact that all the edges fail with an identical probability is not crucial at all. Everything that I talk about extends fairly easily to the case where every edge has its own failure probability. Okay? And then given this setup, I'll call the unreliability of a graph, denoted UG of P, as the probability that the random graph GP is disconnected. Okay? That it splits into multiple pieces. And the all-terminal network unreliability problem, I'll often call this just network unreliability. I'm not going to talk about anything other than the all-terminal version. This problem is just given a graph G and a probability P, estimate this value UGP, estimate the unreliability of the graph. Any questions about the problem definition so far? Right, so if there are no questions, let's keep going. So what's known about this problem? So going back 30 years, maybe more than 30 years, 35 years, this was one of the problems that were used to introduce the complexity class sharp P. So in this seminal paper of Valiant, where he introduced the sharp P class, he showed, among other problems, he showed that the network unreliability problem, the all-terminal version, is sharp P complete. So the problem is hard. We don't expect to be able to solve it exactly. We don't expect to get algorithms that precisely figure out what the value of UGP is. And then there is this follow-up work by Broaden and Ball, which kind of hints at what happens if you allow approximations. And they say that in general, if epsilon is allowed to be any arbitrary value, and I assume they mean exponentially small values, then you can't really do anything. But they add this footnote which says we should note that a seemingly more difficult unsolved problem involves the case when epsilon is constant, i.e. is not allowed to vary as part of the input. So in today's language, we would say, well, it's possible that we can get a p-task for this problem, but we don't know. That was the state of the art. And then the next couple of results are so the next couple of results are about specific graph classes. So Karp and Luby looked at this problem on planar graphs with the assumption that the number of edges, the expected number of edges that are failing is small. Okay, so P is chosen in a way that the number of edges that fails is at most log n. Under this assumption and the structural assumption that the graph is planar, they obtained some approximation algorithms to estimate UGP. And of course, instead of talking about the probability that the graph gets disconnected, you could also talk about the probability that it stays connected. So these two things are complementary to each other. If you're thinking of exact algorithms, these two are equivalent. If I have one of the values, I have the other one as well. But since we are talking about multiplicative approximations, these are two different problems. And this other problem, the complementary problem, is called the reliability problem. Allen, Fries, and Welch looked at the reliability problem, but only in dense graphs. So they gave approximations to reliability if the minimum degree of the graph is very large. It's omega of n. Okay, so that was the state of the art going into the mid-90s. And an interesting anecdote is, so yesterday we were discussing what's sort of the future of the field, what are important problems to consider, things like this. For this problem, there's an interesting connection to this. So in the mid-90s, apparently in a plenary talk at Stock, I think, or Fox, Ravi Kannan was trying to answer the same question, what should graph algorithms be looking at, what are some interesting problems? And he said, this is one of the outstanding questions in graph algorithms. Can you get a general algorithm for approximating the unreliability of a network? Yeah.
So when you are talking about the network unreliability problem, the expected output of probability.
Yeah.
So this probability has to be a rational number.
Yeah. So
Okay.
it's a value.
It's a value.
Yes. It can be exponentially small.
Okay.
Yeah. So P, I mean, I'm assuming P to be rational. It's
Okay.
finite precision. And then U is well defined and has finite precision, but it could be exponentially small in the parameters of the problem.
Okay. So when you're talking about the sharp P completeness, you're talking about this model.
Yes. Okay, so the story goes that Ravi Kannan mentioned this in a talk at one of the major conferences and proposed that the community should be looking at this. And like many problems in graph algorithms, David Karger got interested and he figured out the solution. So the first general algorithm for this problem is due to Karger. So he gave a fully polynomial time randomized approximation scheme for estimating UG of P. So what that means is that the algorithm will give you a 1 plus epsilon approximation for an arbitrary value of epsilon. The running time is polynomial in the size of the graph and this parameter epsilons, or 1 over epsilon. It is a randomized algorithm. It's also Monte Carlo, so there's some small failure probability of the algorithm. There's some small chance with which the algorithm is not going to give you the right answer. And the algorithm runs in time. If you sort of drill into that paper, you see that the algorithm runs in time that's about m times n to the 4. Okay, so I'm omitting the dependence on epsilon. I'll more or less think of epsilon as a constant throughout this talk. All of these papers actually precisely figure out the dependence on epsilon, but to keep things simple, let me omit it here. Okay, so about n to the 6 running time. It's not the fastest polynomial time, but it's a polynomial time algorithm. Yeah.
This is a relative approach, like 1 plus epsilon.
It's a multiplicative approximation, yes. Other questions? Okay, so then there was again a lull for a few years, and then Harris and Srinivasan, David Harris and Irvin Srinivasan, they picked up this problem. And they asked, can I do anything better? Can I get a faster algorithm? As I said, it's a polynomial algorithm. Karger's algorithm runs in polynomial time, but it's not very fast. And they analyzed the same algorithm, exactly the same algorithm that Karger had, but they showed that the analysis that Karger had is slack. And they could improve the analysis so that the running time went from n to the 6 to essentially n to the 3 with some lower order terms. Okay, so that was the first improvement. And I guess that got Karger interested in the problem again 20 years later, and he realized he could do better. So the running time improvement is small, so it went from n to the 3 plus little o of 1 to n cubed times some polylog n. So some subpolynomial term was being replaced by a polylog term. But the importance was now he changed the algorithm. So this is no longer a better analysis of the previous algorithms, but a completely new approach to the problem. And we're going to look at all these approaches in this talk. So he proposed this new algorithm that uses a very different way of thinking about the problem, and that gets the better running time. And then in a sequence of works, he realized how to refine this new approach and eventually brought down the running time to n squared. And this refinement in some ways is somewhat reminiscent of what Sanjeev talked about yesterday. So this first algorithm sort of used a two-step process, and they were using a gadget to solve the second step. These later algorithms replace the gadget with a recursive construction, and that improved things a lot. Okay, so that was the state of the art around 5 years back. And that's when we started looking at this question. Now, what I'm going to tell you later is that there's something special about this time n squared. And for those of you who are familiar with this, a graph that's very sparse, has only n edges, can have n squared minimum cuts. And if you think of what you are doing in trying to figure out unreliability of a graph, there is a sense in which you are counting minimum cuts. You're trying to figure out how many minimum cuts or how many small cuts are there. You're trying to somehow count. If a graph has a lot of small cuts, unreliability is likely to be small, whereas if a graph has a lot of small cuts, maybe it's large. So at least in some intuitive sense, n squared is a natural target to shoot for. And I'll make this a bit more formal later. So it wasn't clear whether you can actually overcome this, whether you can get a running time that's smaller than n squared. And what I'm going to briefly talk to you towards the end are ways that you can actually do that. Okay, as I said, much of the talk will be a sort of survey where I talk about what was happening in this problem in the last 20, 30 years. But then towards the end, I'll show that, in fact, you can get running times that's like n to the 3 halves. So we go from an n squared running time to n plus n to the 3 halves. Of course, if the graph already has n squared edges, you can't really do very much, but if it's sparse, then you can do better. So this was last year, and then this year we figured out, in fact, you can actually solve the problem in almost linear time. And up to this lower order term, now the problem is resolved. Again, questions? Stop me anytime. Anything that's not clear, just stop me. I don't have a very long talk, so I can take as many questions as you want. Yeah.
So is M a natural lower bound for this problem?
That's right. You need to read in the graph. Even finding a single min cut, you need to read in the graph.
This is even in the randomized setting?
Yes, even in any setting. Yes.
So I guess you use max flow here, right? Like
Yes.
for there's a max flow with that running time on the top too. So does it mean that you stop 25 results at a subsume the soda paper as well?
Well, I mean, the m to the little one comes from various sources. One of the sources is max flow, but there are other sources. There's recursion that actually has that form. So. Any other questions? All right, so let me go back and start with what was the original idea that Karger had for this problem. That's where everything starts. All of the subsequent algorithms build on those original ideas. And the original idea is actually very simple. So if you think about it, when is a graph disconnected? So if g of p is disconnected, it must be the case that all the edges in some cut must have failed. Okay, this could have happened for many different cuts, but it has to happen for at least one cut for the graph to get disconnected. So now you might want to try and capture this event that all the edges of a cut failed by defining Bernoulli random variables indicating whether a specific edge failed or not. So for edge E sub I define a random variable x sub I, and x sub I is 1 with probability p, and this indicates that the edge has failed. Okay? So now using these variables, I try to capture the event that an entire cut has failed. So let's fix our attention to one of these cuts. Let's say the first cut. So this cut, let's say, has 3 edges, EI, EJ, and EK. I have 3 corresponding variables, x1, xi, xj, and xk. What does failure of the cut mean? It means that all of these 3 variables realize to the value 1. Okay, so I can write this out as saying xi and xj and xk. This event exactly characterizes the failure of the cut. And I can now go enumerate over all the cuts in the graph. For each cut, I can write this event that indicates failure. And I can take an OR over all of this, and that simply indicates that the graph has gotten disconnected. Okay, this is completely lossless. I've just rewritten what it means for a graph to get disconnected. Okay, here's a simple example. I think all of you probably already understood what I described here, so I won't go over the example again. All right, so you can write this formula. And then, therefore, the problem of figuring out the probability that the graph gets disconnected is the same as figuring out the probability that this formula, I'll call this the cut formula, evaluates to true when every variable is an independent Bernoulli variable. Okay. Now, thankfully, this is a problem that has been studied in the past. So if you looked at that formula, oops, let me go back to the formula. Yeah, so if you look at this formula, this is written in DNF form. Okay? And if you have a formula, Boolean formula in DNF, then we are asking, given a DNF Boolean formula, if every variable is an independent Bernoulli, what is the probability that the formula evaluates to true? This is a classic problem that was considered by Karp, Luby, and Madras, and they gave what is really a very beautiful and classic algorithm using importance sampling to estimate this probability. Okay, so this is something you can estimate, approximately estimate. Okay, but that doesn't solve the problem entirely, because the cut formula itself is exponentially large. There are exponentially many cuts in a graph. So if I just naively use this formula, I'll have an exponential running time just because the formula is too large. And this is really where Karger's main idea comes in. And what he says is that, well, there are two types of networks. Either a network is unreliable. So what that means is that it has a reasonably high chance of getting disconnected. These are easy networks, and we'll see why these are easy. The difficult network is when the network is really reliable. The network doesn't really get disconnected. There's a very small probability I'm trying to estimate. But if I give you a reliable network, what am I trying to figure out? I'm trying to figure out whether a cut in that network has failed. What Karger says is that you can actually only focus on a small number of cuts. You can only focus on the cuts that are small in size. Now, of course, small cuts have a larger probability of failing than large cuts. But a graph has a lot of large cuts and few small cuts. So this is not completely obvious when you first look at it, that you can ignore all the large cuts and simply look at the small cuts. And this certainly needs a proof, but that's the main fact that Karger proved in his paper, that you can ignore all of your large cuts, simply focus on the small cuts, and that will give you a good enough approximation. And once you have this, the rest of it is fairly straightforward. So many of you might be familiar with this, something called a cut counting lemma. This says that if the minimum cut of a graph is of value lambda, and if I fix any parameter alpha, then the number of cuts that are of value at most alpha times lambda is not large. It's only n to the order alpha. So which means if I can fix my alpha to be a constant, if I say that the only cuts I care about are cuts that are, let's say, at most 4 times the minimum cut, then the total number of cuts I need to care about is polynomial. It's just n to the 8 if alpha is 4. Okay? So you can truncate your cut formula. You can take your large cut formula, truncate it at only the cuts that are, let's say, 4 times the minimum cut, and throw away everything else. It doesn't matter. Those don't matter. Yeah?
Are we low weighting the probabilities when applying this?
One more time, I didn't quite get the question.
So are we applying, are we, what are the weights of these? Is this just the probability or the log of the probability?
So the edges don't have weights per se. Every edge either survives or fails, and the failure probability is P.
Because you're taking
minimum cut means number of edges.
Just number of edges. Yeah, there's no weights. By minimum cut or approximately minimum cut, I just mean counts on edges. Okay. Thank you. Other questions? Okay, so you can take your giant cut formula, truncate it beyond to just a polynomial size, and then apply the Karp-Luby-Madras sampling algorithm, and that's what gives Kargar's result. Now, of course, there's one assumption I made at the beginning of the slide, which is that the network needs to be reliable for the first statement to hold. The network is really unreliable. It's not true that you can only focus on the small cuts. But unreliable networks are easy. Any of the students here wants to say why they're easy? Yes?
Just experiment.
That's right. You can just sample. You can do what's called Monte Carlo sampling. You can generate a lot of samples of G of P. The event that the network fails is not an elusive event. It's an event that you will actually witness. And then you can just simply use the relative frequency with which you are witnessing the event. Okay? So unreliable networks are pretty easy. Only simple Monte Carlo sampling works. You had a question?
So we say small cuts. How small is it?
Yeah. So for instance, if it's 4 times the size of the main cut, that suffices.
If the probabilities are not all uniform,
Yeah.
how will you use this thing?
Right. So one way of thinking about non-uniform probabilities is that you can simulate it by parallel edges, each of which has the same probability on it.
You can also enumerate this list of small bits because for the DNF
That's right.
formula you have to.
That's right. Yeah. So that's what the algorithm exactly will do. It will enumerate the list of small cuts. There are many algorithms that can do that, and then you write the DNF formula and apply the Karp-Luby-Madras. Yeah.
So how do you know that which case you are reliable or unreliable?
Yep. So you can distinguish between the two cases by just looking at the size of the minimum cut. So P raised to the size of the minimum cut is a lower bound on unreliability. That lower bound is precise enough to distinguish because up to polynomials the lower bound is calculated.
Just by Monte Carlo sampling, we can see whether it's reliable.
You could also experiment if you want.
How fast is DNF counting actually? Is it linear time?
No, it's not linear time. I think it's maybe mn squared or something like this, like n being the size of the formula and n being the number of variables, something like this. I don't remember exactly.
So all of the modern algorithm avoid this thing.
They will avoid explicit DNF sampling.
So
Yeah.
So if we ever get a better DNF counting algorithm,
Yeah.
better than Karp,
Yeah.
will it help in like reducing the complexity of this algorithm?
Not in this framework because you still need to enumerate all these small cuts and write out this large formula. Okay? So no other questions? Let me keep going. So that's sort of the first generation of algorithms. Now what's happening in these sort of second generation of algorithms? And these will take a very different view of the problem. So what was the problem with these elusive events? If the probability of the graph getting disconnected was small, then we didn't know how to generate a sample of G of P that actually witnesses this bad event, right? That was the problem because of which we had to go through this entire detour. So let's zoom into this process of sampling a copy of G of P. Okay. So what are we doing? We are assigning independent uniform random variables. Again, uniform is not so important, but independent random variables. Let's call these R of E between 0 and 1 to every edge. And we are deleting every edge where R of E, this random variable I'm drawing, the uniform random variable, is less than P. Okay, that's just a sampling redefined. And then we are asking, after these deletions, does the graph stay connected? An equivalent way of thinking of this is to do exactly the opposite. So instead of asking whether R of E is less than P, we ask if R of E is greater than P, that's just a complement event, and if so, let's contract the edge. And then ask if the entire graph has gotten contracted into a single vertex. Right? This is exactly the same as asking whether the surviving edges form a single component. Okay, so here's a picture. I have this entire scale from 0 to 1. Each of these edges land somewhere on this scale because of the random numbers I've generated. There's this fixed threshold P that's given as part of the input. I could either delete stuff below P and ask if the remaining things form a connected component, or I can contract everything above P and I can ask whether I have a single vertex or not. Okay? All right. Now, of course, the main challenge is that the variance of this estimator, so there's an estimator here, right? I can generate G of P and use an indicator variable to indicate the event that G of P has contracted into a single vertex or not contracted into a single vertex. And that indicator variable will give me an estimator for U of G of P. The estimator is certainly unbiased. But the challenge is that the variance of the estimator is very high when P is small, when the unreliability of the graph is really small. Okay? So we need to somehow cut the variance down. How do we do that? So let's do the following. Instead of setting this single threshold P, let's create an artificial threshold Q that's above P. The artificial threshold is set in a way such that G of Q is actually an unreliable graph. Okay, in particular, we'll set Q such that U of G of Q is around 1 over n squared. Okay, so if P were equal to Q, this would be the easy case because you can actually witness the disconnection event. But for now, this is just an artificial threshold. But the good thing is, on the way to contracting all the edges that landed above P, I also contract all the edges that land above Q. Okay, so in this example, both E2 and E3 landed above P, but only E3 landed above Q. So let me go ahead and contract the edges that ended up above this higher level Q. Okay, that's something I can do without affecting anything because even my actual sampling event would have contracted those edges. So I contract those edges and I form this new graph that I call H. Now, can any of you tell me what am I trying to find in H? What's an estimator on that's defined on H and estimates the unreliability on the original graph G?
You readjust the failure probability and compute the reliability.
That's right. You readjust the failure probability and you can compute the reliability. So instead of now using a failure probability of P, I should use a failure probability of P over Q, okay, conditioned on a particular H having been generated. And that estimator of U of H with the new probability value P of Q will exactly be the same estimator that I had initially, U of G of P. Okay? But of course I know that this is something that has high variance. I want to cut the variance down. So I do something that's very natural to reduce variance, which is I repeat. So instead of creating one such H, I create two such H's and I repeat independently on those two copies. And then whatever estimators I get from the from H1 and H2, I take the average of those and send it back up to G. Okay? Does the process make sense to everybody?
Each one is constructed using different values of
No, it's the same value of Q. We just create one H, then you create two copies, H1 and H2, and from now on everything will happen independently on the two copies.
This is somehow doing better than like the first, like trying to do repetition at the first level.
Right, and I'm going to comment on that. So as Siddharth asked, what have I actually gained by doing this, right? Well, what I have gained is that H is a smaller graph. I am repeating, but H is not as large as G because I contracted a bunch of edges. And if I can somehow play with my parameters correctly, I'm hoping that I've contracted the graph down sufficiently that making 2 copies doesn't cost me as much now. So for anyone who is familiar with this kind of technique, does this remind you of anything? Any algorithm? Yeah. Exactly. This is exactly the same idea as recursive contraction in Karger-Stein. Okay, and as I said, the key advantage that H is smaller than G. So repeating on H is more efficient than repeating on G. And in fact, almost exactly the same math as recursive contraction as Karger-Stein works here as well. And that's where the eventual n-squared running time comes from, because the recursion in Karger-Stein ends up with an n-squared running time. Okay, so this is the entire sort of idea of this second phase of algorithms for unreliability. Any questions? Yes?
Can you give some intuition for why we have P over Q as the parameter?
Right, because you already have, so think of it in 2 stages. If I want to sample an edge with probability P, I could first toss a coin with probability Q, and if that coin turns up heads, I can then toss another coin with probability P over Q.
But I'm also deleting, right?
So in this process, I'm not deleting anything. I'm just contracting stuff from the top. Okay, but instead of contracting everything down to P in one go, I'm contracting down to H first, then creating multiple copies, contracting down further in the 2 copies in the next stage, again recursively constructing more copies, etc. Yes?
How does one find such a queue?
So that's part of the analysis, so that's reverse engineered in the analysis. It turns out that the right queue, because you're trying to balance 2 things. You want to balance the size of the graph. The more aggressive your choice of Q is, lower the choice of Q is, the more aggressively the graph will become smaller. But on the other hand, if you choose a really small value of Q, then you'd be left with a very unreliable estimator, something that has very high variance. So you will need to repeat a lot of times. So you need to balance these 2 things, the variance and how much gain you are getting out of contractions. Yes?
So this estimation that's done recursively, that's still using that Cart-Luby idea, DNF.
No, there's no Cart-Luby anymore. This is just completely recursive.
So the estimation that we are doing, what's the estimate again?
So on this, so you have the same, you now have a new graph H1, a new graph H2. On these, you want to estimate unreliability U of H1 or U of H2.
What is the estimator here?
So the estimator is the recursive value of, you run the same algorithm recursively on these new graphs.
Do you mean UH1 plus UH2
Divided by 2, yeah. Eventually, when you create 2 copies, you will take the average of what you get out of the 2.
For a single copy, what's my estimator?
It's exactly the recursive estimator on this smaller graph with the different probability. It's just recursion. It's the same.
I get it.
Yeah, same algorithm.
So how far down the recursion do we need to go?
You need to keep going until you are down to this level, down to the original probability P. And then you figure out if it's disconnected or connected. Right? Once you are down here, P of Q, that thing will become 1. So now you have, you know the actual value. You don't need to go any further. It's either 0 or 1.
Choosing a Q such that the estimate is close to 1 or n square is easy.
That's something you can do. Again, you can use the fact that the unreliability is up to a polynomial. It's kind of approximated by what's happening on just one bin cut.
So you're saying you will stop when the network becomes unreliable?
No, you'll stop once you, so think of it as going down levels here. You'll stop once you hit this current level.
So
P.
Q approximately equal to P.
Yeah, you will stop once that quantity, the P over Q, this quantity becomes 1.
So that's kind of like Q approximately P. So that means that this
Yes, but I'm showing this in two stages. What's really happening is a full recursion. So if there's a Q1, then a Q2, then a Q3, etc. And the product is what matters.
So you'll be running approximately n square many steps, right?
So the entire recursion will take n squared log n time,
N squared.
or n squared polylog n time. Yes?
How does H1 and H2 differ?
They are exactly the same, but then on H1 and H2 will run two independent random processes. So their estimators that they return may not be the same. The graph, structurally the graphs are exactly the same. More questions?
So this 1 by n square can be like 1 by n cube also? Like,
That will change the running time. Correctness will be fine. 1 by n squared is the sort of sweet spot that gets the best running times.
Just one last question. How many copies do you actually have to make?
So that depends on what that quantity is. That depends on what this quantity is. But if you choose this to be 1 over n squared, it's 2 copies in every step.
So when the probabilities are non-uniform, what is
Again, so if probabilities are non-uniform at the very beginning, you can simulate it by a different graph where the probabilities are uniform. Alright, so hopefully it's at least at a high level clear what's going on. So as I said, this leads to this quadratic barrier. And the estimation of UG of P is conceptually related to counting minimum cuts. Because somehow, as I said, every minimum cut is the most likely to fail, and if you have more minimum cuts, then the overall the graph is more unreliable. And in principle, both the first and second generation algorithms, both the techniques I showed you, count minimum cuts by enumeration. The first generation algorithms do this explicitly. So you actually enumerate all the minimum cuts and near minimum cuts exactly. The second generation algorithms are, as I said, they are very similar in a very quantifiable way to recursive contraction. And recursive contraction algorithms can be used to enumerate all minimum cuts. So implicitly, they are also able to enumerate minimum cuts. Now the problem is that a graph can have n squared minimum cuts, even if the graph is very sparse. Just think of a cycle. Okay, and an nh cycle has n choose 2 minimum cuts. So if you have such a graph and your algorithm is explicitly is able to enumerate the minimum cuts, then your algorithm is not going to run any faster than n squared. Okay, so this enumeration of minimum cuts is a major bottleneck. It's a real bottleneck for both these classes of algorithms. So somehow, if you want to get better running times, we need to get around this. We need to be able to figure out a way to estimate unreliability without actually figuring out the minimum cuts of the graph. Okay, so our contribution in the first paper, and this is what I'm almost, I'll spend most of the remaining time on, is to figure out a new estimator for unreliability. And this estimator is explicitly tuned to avoid counting minimum cuts. Okay, I'll explicitly try to stay away from algorithms that are able to count minimum cuts. Now let me start off by two simple observations. The first one is something I've already talked about. You can discard large cuts, right? This was in the first algorithm already. You don't really care about cuts that are large. Now here's a second observation. So even if you discarded all the large cuts, after that you were doing DNF counting. So this is some kind of inclusion-exclusion that you are trying to estimate. But really, what are you really counting? You're counting all these events where a single cut fails, then all the events where 2 cuts fail, 3 cuts fail, etc. But your graph is very reliable. The chances that 2 cuts will fail is tiny compared to the probability that a single cut fails. So in fact, we show that it's sufficient to just think of single cuts failing. The contribution of multiple cuts failing is tiny in reliable networks. What's the advantage of doing this? The advantage is that now you, instead of inclusion-exclusion, you can just use a union bound. Right? I can think of what's the probability that cut 1 fails, what's the probability cut 2 fails, and so on. And then I don't really need to figure out what kind of interactions happen, I can just add up these probabilities. because all these interactions are going to be really lower order events. Okay? So that says that what I am now trying to estimate, modulo these two observations, is this quantity which we call Zp of g, which is the sum over all values of alpha, let's say between 1 and 4, where for each value I take p raised to alpha times lambda. This is the probability that a single cut that has alpha times lambda edges fails, right? There are alpha lambda edges, each edge fails independently with probability p. So this is the probability that a single cut fails. And this is just a count of how many cuts I have whose size is alpha times lambda. Okay, so we are trying to estimate this quantity, this relatively simpler quantity than what we started with.
It's like partition function.
Yeah, you could think of it that way, yes. Okay? Yeah, the way I think about it is it's a union bound. I have replaced all this like complicated thing by just a union bound. Okay, now our job is not done because although I have simplified my expression, the number of cuts that are involved is still very large. I still have n to the 8 cuts if I am going all the way to alpha equals 4. Right? So I can't do an explicit estimation of this. I can't sample cuts and just explicitly try to estimate this quantity. There are just too many cuts here. So I would like to have some way of sampling these cuts, or cuts of value at most 4 lambda, and use p raised to the size of the cut as the weight of a sampled cut, but I don't want to do this explicitly just because there are too many cuts in my set. So what do we do? So what comes to our rescue is a theorem of Nash-Williams and Tutt. I think this has also been mentioned on and off during the workshop. This theorem says, at least the form of the theorem that's useful for me, says that if a graph has a min cut of size lambda, then there are at least lambda over 2 edge disjoint spanning trees in the graph. Okay? And the number can range between lambda over 2 and lambda. Why is this useful? So let's think of the following sampling algorithm. Let me construct lambda over 2 edge disjoint spanning trees. Okay? Now let me take a cut of value at most 4 lambda. This cut has only 4 lambda edges, and all my spanning trees are edge disjoint. So these 4 lambda edges will have to spread out among these cuts, among these spanning trees. So on average, any such spanning tree only receives at most 8 edges from any such cut. If I fix any cut of size at most 4 lambda, it contributes on average at most 8 edges to each spanning tree here. Okay? So maybe I can expand the set of cuts I'm looking at even further by looking at all the cuts that have 8 edges in a randomly chosen spanning tree from my packing. Okay. So let me show this through a picture. So I started with cuts of value at most 4 lambda. I want some way to sample these cuts. I don't know how to efficiently sample such cuts. I'm expanding it to this larger set of cuts that's 8 respecting in a random spanning tree that I draw from this collection of lambda over 2 spanning trees. And you can make this a little more robust by taking log n spanning trees instead of just one random spanning tree. Okay? And this is something, if I have given this collection of spanning trees, if I have some way of sampling a spanning tree quickly, then this is something that I have sort of better algorithmic control over. I can do this very fast. Figure out 8 random edges in the spanning tree, and that gives me my cut. Okay, so the first question, I still don't know whether this is useful in terms of actually estimating my quantity Zg, but at least can I do this efficiently? And we show that indeed you can. So there is a sampling algorithm that we designed that runs in polylog time, and you can sample cuts from this larger set of 8 respecting cuts. So at least I have some efficient way to sample cuts. If I just stuck to these cuts of small size, I have no efficient way to access those cuts. I have no way to figure out whether how I will get to a cut that's small without avoiding the large cuts completely. Yeah.
The statement was 8 on average. And
Yes.
here you are imposing 8 strictly on.
That's right. So this distinction is not so important because instead of taking one sample, I can take log n samples, and then essentially every cut will have the property that in one of those samples it will have a size of 8. Yeah. Yeah, we actually avoid all that. We just go straight to the cut. This is what's happening sort of in the analysis that certifies that this algorithm is good, but the algorithm just samples directly. Yeah.
So does this union bound argument still continue to hold when we go down to these respective cuts? Because we could have like
That's right. So I'll get to that. Okay. So the question is, doesn't this distort your estimator? How is the estimator unbiased? Okay. So one thing that we show, and maybe that's going to appear later, but let me answer you. One thing that we show is that we can quickly compute weights, a new set of weights for these cuts that I'm sampling from, that keeps the estimator unbiased for the original set of cuts. Okay, so but that's non-trivial. That's not something that's immediate. All right. So, but here's a bigger issue. What if this set, the set that I'm really interested in, look, these cuts, the cuts that are in the difference of these two sets, are kind of useless to me. I don't want to spend time on these cuts. It's just that it's easier for me to sample from this larger set. Now, if that dark blue set is large compared to this light blue set, then it doesn't matter. If that dark blue set is, let's say, has half the measure of the light blue set, then half the time I will sample some bogus things, but it doesn't really matter to me. But if that dark blue set is really small, it has really small measure in this set, in this collection, then I'm mostly going to spend my time sampling useless things. And I'm never going to get a good estimator for what I'm looking for. Okay? So what do I do if that happens? Now, thankfully, if that happens, we can show that most pair of vertices are very well connected in the graph. So all these 4 lambda cuts, they don't separate most pairs of vertices in the graph. They only separate the graph in some very specific places. And then there is some sort of more messy thing. You can then construct what's known as a Gomory-Hood tree and reduce the size of the graph by contracting away all these pairs that won't contribute to your 4 lambda size cuts. Okay? So there's some way that you can pre-process the graph such that this dark blue set is actually large compared to the light blue set. Okay? So let's put all this together. So in reliable networks, roughly if the unreliability is less than 1 over n cubed, we have now given this new estimator for this quantity p of g. Actually, that should be zg of p, I guess. Yeah, zg of p. That just captures the union bound over the first 4 lambda cuts. That can be approximated fast, can be approximated using m times n to the 3/2 time. And n to the 3/2 just comes from how many cuts I need to sample from these spanning trees in order to get a good estimator. Yes?
So when you get these cuts of size at most 4 lambda,
Yeah.
this distribution might be very non-uniform.
That's right. So you have to reweight the cuts. So every cut that you get, you need to reweight it. You can't uniformly weight all the cuts and get an unbiased estimator from the original quantity. You need to reweight it.
And also, even if the estimator is unbiased, there can be variance.
Right, and n to the 3/2 is exactly the amount of repetition you need in order to cut that variance down. Other questions? All right, and then we also need to work in the other part of the algorithm that I didn't have time to go over it. But it's not enough to just get this fast estimator for the reliable case, because even the unreliable case wasn't as fast as what we wanted in the previous algorithms. So here we have to change the recursive contraction algorithm in some ways so that we can get a faster running time. Okay, but we don't generally, like in a general sense, we don't improve recursive contraction. Recursive contraction is still n squared. In fact, you can't improve it. But we use the fact that in graphs where you have this property that they're unreliable, there you can do something to recursive contraction to make it a bit faster. Okay? All right, so I think I'm running out of time, so maybe I'll skip this, but I'll say a couple of words about what was on the next 3 or 4 slides. So one other direction you can think of is what happens if it's a hypergraph instead of a graph. And so the problem is that you are given a hypergraph, and every hyperedge in that graph fails independently with identical probability. And you can ask exactly the same question: can you figure out what's the chance that the hypergraph disconnects into 2 disconnected parts? So we looked at this with Roshu and Jason. And the main challenge is that now once you get to hypergraphs, truncation of the cut formula is useless. Because on hypergraphs, it's known that although the number of minimum cuts is just n squared, the number of near minimum cuts, if you go slightly above minimum cuts, it's already exponential in the rank. So you can't, although you're allowed to truncate, the truncation doesn't reduce the size of the cut formula, it keeps it exponential. Okay? So hypergraphs are a different beast, and I don't know of a polynomial time algorithm yet to estimate unreliability in hypergraphs, but what we managed to do is to get a quasi-polynomial algorithm, and there are sort of 2 variants of whether it's quasi-polynomial in terms of hyperedges or in terms of the number of vertices and so on. And I'll let you stare at this for a second and move on, just in the interest of time. All right, so let me skip this. And of course, the natural question is, can the running time be improved to polynomial? Yes?
So for this hypergraph, where you failed with this slightly larger than minimum curves, is the issue that the hyperedges can be very big. If you have a small uniform, like 3 or 4 uniform hypergraph, we have the same problem.
That's if it's 3 or 4 uniform hypergraphs, then you can extend the graph techniques. So if the rank is small, then you can extend the graph techniques. Large ranks are the problem. But I mean, it's not very robust in the sense that you can extend the graph techniques, but only if the rank is constant or something like that. Already at root n or something, like at little of n values, it's already a big problem. All right. Okay, so let me end with a couple of open problems. So my first open problem is, can we do anything at all for reliability? So I've been talking about unreliability, which is the probability that the graph gets disconnected. You can think of the complementary problem of what's the probability that the graph stays connected. There are a couple of algorithms at this point that give approximation schemes. The first one was by Mark Jerome and Guo, and then there was a follow-up by Feng and Guo. But both of these use Monte Carlo techniques, Markov chain techniques, and they are not efficient. Certainly not anywhere close to being as efficient as the unreliability algorithms. So we don't know how to do this more efficiently. And another interesting question I want to pitch to maybe students who are looking for a problem to think about, what about the 2-terminal version of this problem? So if you look at Valiant's paper from 1979, he shows that two different versions of the unreliability problem are sharply hard. First is all-terminal network unreliability, which I talked about. The other one is, I have 2 fixed vertices S and T. Every edge is getting sampled with probability P as in our model. What's the probability that S and T get disconnected? Okay, and for this problem, I don't know of any non-trivial approximations, and certainly no approximation schemes. Okay, so that's I think an interesting question. One of the sort of conceptual challenges is that unlike for global minimum cuts, there can be a lot of ST minimum cuts. There can be an exponential number. So anything that's kind of enumerative is going to run into a lot of problems. All right, so that's all I have. Thank you.
How different is the absolute version of the problem where I want a plus minus epsilon error?
So the absolute, like additive errors make a problem a lot easier because now you only care about the case where the unreliability is large. So it basically reduces to the unreliable case we can do something. Yes?
So anything for reachability for directed graphs in this way?
Yeah, nothing's known for directed graphs. Directed graphs seem to be an even harder question to answer. Well, you can ask for reachability, or you can ask for even things like strong connectivity, and I don't know of any results. I don't know, Thachapol, if you know any hardness for reachability. Reachability might even be hard, I'm not sure. There is one result for DAGs. There's something known, some relatively weak results known for DAGs.
So what is it trying to?
Whether the DAGs still remain like, I think whether it remains weakly connected or something like that.
What are some other problems studied in this graph estimation? What would say like number of selected components?
I mean, things like counting the number of matchings, perfect matchings in a graph and so on have been, like that, those are classic problems as well. Number of minimum spanning trees, I think, has been. Yes?
In hypergraph setting, is there a possibility of approximation hardness?
Yes, there is. And
PX hardness?
yes, maybe based on ETH or, I mean, some versions of these problems. For example, if you go a little beyond hypergraphs, then even the min cut, there's something called hedge connectivity, and there even the min cut problem has ETH hardness of possible, like there's a quasi-polynomial ETH hardness. So it's possible that there's hardness, yes. But for hypergraphs, I don't know of any obvious barriers that you know of. Right, so if there are no other questions, thank you.
Is your result on hypergraph like? This is yours. I was about to take it and
Sorry. Oh, okay.
A quick reminder to all the juniors, please sign up for the junior senior lunches. The lists have been put up outside.
So is your result on hypergraph actually connected to edge version or?
I didn't think very hard about it, but I don't know. At least it's not like it's not complete immediate. Like maybe the techniques will work, but not immediate. Like hedge is interesting because hedge gives you dependence. Like everything here is independent. You can think of hedge as some kind of dependent.
Yeah.
So it might be interesting.
Do this demonstrated business, you define the sketch and
Welcome you all for the next session of the workshop. I'm honored to introduce Dr. Amit Chakrabarti. He's a professor at Dartmouth College. He's interested broadly in theoretical computer science, specifically in complexity theory, data streaming, and also in algorithm, especially for efficient processing of big data and hardness of approximation. He received his PhD from Princeton, and he is recipient of multiple prestigious awards, including Fox 20-Year Test of Time Award in 2021. Today, he'll shed some light in graph coloring problem in the context of streaming, communication, and robustness. Without further ado, we'll hand over to Dr. Amit Chakrabarti. Thank you for being here, sir.
Thank you. Yeah, well, thank you to the organizers for making me a part of this wonderful workshop. It's been great listening to all these wonderful talks, and they are a hard act to follow. I shall try my best. Feel free to stop me with questions if you have any, especially in the initial part of the talk where we're defining things slowly. Okay, so this talk, as you can see, is about graph coloring. I'm sure you've all encountered graph coloring before as a concept, but just to be sure that everybody is on the same page with regard to terminology, here's a small example introducing all the things. So we have a graph, and the goal in graph coloring is to assign colors to the vertices of this graph so that no edge is monochromatic, meaning no two adjacent vertices get the same color. This is a central problem in graph theory on the combinatoric side and also on the algorithm side, trying to find algorithms to produce good colorings. What is a good coloring? So a coloring that uses as few colors as possible is what we think of as good. So we use the word palette to refer to the set of colors. So here the palette is just the integers from 1 up to p. It may as well be. The names of the colors obviously don't matter. We call a coloring proper if it assigns distinct colors to the endpoints of every edge. The chromatic number of a graph is defined to be the smallest palette size for which a proper coloring is possible. And we know, you should know, I'm sure you know, that it is NP hard to approximate the chromatic number of a graph, and in fact, even a very weak approximation is NP hard. Okay, these are classic results in complexity. Now, this talk is not about chromatic number. Okay, so I'm not going to be interested in coloring a graph with the smallest possible number of colors, which is anyway a very hard problem. We're going to allow a much larger palette, which makes it possible to just color the whole graph in linear time because there's so many colors available, right? Okay, now when I say linear time, I do mean linear time in the classic computational model that you would have studied in your first algorithms course, okay? So, what is such a large palette that definitely allows a linear time algorithm? So let delta denote the maximum degree in the graph, and I claim, and it is very easy to see, that if I allow you delta plus 1 colors, then it's guaranteed that there will be such a coloring, and you can find it very easily by using just a greedy algorithm. So in this example, yes, delta is 4. If you look carefully, the maximum degree of a vertex is 4. And indeed, the greedy algorithm will say just, color the vertices. Suppose we've colored some of these vertices, and now we're considering this guy over here. Just give it any color that's not yet being used by its neighbors. There's guaranteed to be one anyway because there's delta plus 1 color in the palette. So just give it that color, and then maybe you try this vertex next, give it a suitable color. It has to be different from all the ones before, just you can see the constraints imposed by the edges cause you to do that. Then finally you have to color this guy, and you have to use a color different from all of the ones so far. So ultimately you've used 5 colors to color this graph. Okay? And that is indeed delta plus 1. Okay, this is not the best thing you can do for this graph. You can actually do slightly better still with a greedy algorithm. Okay? The thing is that you have to do this greedy not in an arbitrary order that I was doing here, but in a carefully chosen order. You can color every graph with kappa plus 1 colors, where kappa is this parameter called degeneracy. This is a little bit less well known than, say, degree, which everybody knows about. Here's the definition. The degeneracy of a graph is the smallest number k such that every subgraph has a vertex of degree at most k. Okay, that's a bit of a mouthful, so maybe stare at this for a moment. You could convince yourself by just trying a few things out that this graph over here has a degeneracy of 3, I believe. Okay. So, according to this, it should be possible to color it with 4 colors. And what you have to do is color in a suitable order. So suppose you start with the vertices here at the bottom, you have to give them different colors, of course, as you can see, they form a triangle. And now, let's say we try this vertex next. We give it a color different from all three of these, and then this vertex, and we give it color different from all three of these. Importantly, we can give these vertices the same color. And now we find that several colors are possible for the last two remaining vertices. And overall, we've achieved the 4 coloring now. Okay, it is the afternoon of one of the later days of the workshop, which means I'm sure people are starting to feel a little bit tired. You've also just probably had lunch and a leisurely stroll. Time for some exercise. 3 exercises. Okay. Start with a simple one. Do you see that the parameter kappa is always less than or equal to delta? So hopefully if you stare at the definition, you will see this has to be the case, right? Just because of how it's defined. Okay, slightly more interesting. Can kappa be much smaller than delta? Can you think of an example where this happens? Feel free to call it out. Yeah, okay, stars, claws, whatever. Exactly, right. So you can have a vertex with very high degree, but if everything is a star, then the degeneracy is only 2. Okay? Another interesting thing you might want to think about is every planar graph, there's a well-known theorem that every planar graph has a vertex of degree at most 5, and therefore every planar graph is going to have a degeneracy of at most 5. Okay? Whereas obviously the max degree is not bounded in a planar graph. Alright, so kappa could be much better than delta. Okay? Right, third exercise. I said here that you should color the graph greedily using a suitable vertex ordering. Can anybody guess what might be a suitable vertex ordering? And this one's a bit hard, maybe a bit unfair if you haven't seen it before. But what I did here may give you a hint. So you may want to start with high degree vertices, but it's not quite start with the max degree vertex. Okay, so I'll tell you what you have to do here. Peel off the lowest degree vertex in the graph, and then the lowest degree now, and then the lowest degree, and so on. So iteratively peel off the lowest degree vertex in the graph. This forms a sequence of vertices. Now color in the reverse of this sequence, and that will give you a kappa plus 1 coloring. It's easy to prove. Once I tell you that this is what you should do, it's easy to prove. Okay, very good. So far we've been talking about algorithms in the usual model, so to speak, in the traditional models. However, this talk is not about that, right? So the problem is too easy in that model. If we look at all of our favorite sublinear algorithms models, though, then this problem is actually non-trivial in each of them. So what do I mean by sublinear models? I mean things like the local and congest model of distributed computing. Actually, these are the models in which this problem was first studied extensively for many years. And then there's streaming, which is sort of my favorite model among these. There's this MPC model inspired by modern kinds of cloud computing architectures. There's query models, which some folks in this audience care about. I mean, I care about them too, but some in the audience have worked on them extensively. And then, of course, communication, which is another love of mine. Okay, so in this talk, I won't address them all, but I will focus on streaming and communication, which are the things that I know well. Okay, so coloring a streamed graph, all right, this is going to be our main problem of study. Towards the end, I will talk about communication some. And communication is going to show up every now and then when discussing lower bounds, so it's just there in the background. Okay. So you've seen the streaming model several times, so I can go over this quickly, I hope. We have a fixed vertex set. The edges arrive in a stream. You could think of a turnstile stream where edges can both arrive and depart. This aspect won't matter much, so for the purposes of this talk, we can think of the stream as being just a plain set of edges. Notation-wise, there will always be n vertices, maximum degree is delta, so the number of edges is bounded by half n times delta. And in reading the results that are to come, you might want to think of delta as being a small polynomial in n, like n to the alpha, right? More than log n, say. As an aside, it's funny that we call n to the alpha a polynomial. If you go outside of this theoretical CS community and tell them that root n is a polynomial, they're going to ask you, what are you smoking? Yeah. Anyway. In these cases, can we color in sublinear space, right? Okay, so this question was, I guess, asked and addressed by a couple of students of mine, Suman Bera and Pranthar Ghosh, and they had a preliminary result in this, which got subsumed very quickly. So I guess one doesn't hear about it all that much, but I want to give them credit for identifying this problem before other literature existed. But essentially concurrently, Asadi, Chen, and Khanna, Sanjeev is over here, published this landmark result, which arguably is the major algorithmic result in this field. They showed an algorithm which I will show you in a moment. But more than the algorithm itself, they had this beautiful technique that they call palette sparsification, and it gives you an interesting combinatorial theorem. Okay? And that theorem has been very, very useful in subsequent works. Yeah. Okay, so let me tell you about their technique. Right. So at a high level, at least I'll tell you my take on this technique. Yeah. And Sanjeev can tell me if he disagrees with my view of this. So at a high level, we're going to over-constrain the problem so that as the graph is presented in a stream, we need to remember less of it. Okay, so what do I mean by over-constrain? So for each vertex, I'm going to choose a random list or sub-palette whose size is about order log n, right? And now I'm saying I'm going to constrain the vertex v to get a color only from this list LV. Okay, this is extra constraint I'm imposing. Now having imposed this extra constraint, it means I only need to care about edges u and v where the lists possibly intersect. Because if the lists didn't intersect, then the edge places a certain constraint, saying u and v cannot get the same color, but the lists have already enforced that constraint. So I don't need to remember the edge uv. Alright, so just to be sure you have a mental picture of what's going on, every vertex has a randomly chosen list. Okay, and I now retain only a small fraction of the edges, those where the lists have some color in common. Okay, like here and here, there's a green or there's a gray color in common, etc. Right? Whereas between, say, here and here, these two lists have no color in common, so I just forgot about that edge. Okay, what is the probability that I will actually retain an edge because the lists, intersect? The straightforward calculation shows that it is, this expression over here, and this works out to log squared n over delta. Okay, and in terms of how many edges we're retaining, remember there's n times delta edges total. So if you do n times delta times this, then what do you get? You get n log squared n, right? Okay, so we're going to collect n log squared n edges. With high probability, it won't be much more than this. Okay, forget this next gray line for the moment. Now at the end of the stream, having collected the necessary set of edges, we have a list coloring problem, right? So we have a small graph, much smaller graph, but we have a list for every vertex, and we must use a color from this list for each vertex. So this problem is called list coloring, and it could be harder to solve. Actually, that list coloring may not even exist. You have to prove that this random choice of lists actually gives you a solvable problem, right? So this in fact can be proved, and that is probably the meat of the work in this paper, right? It is, I will tell you, difficult to prove. It's quite a beast of a proof. Anyway, but it can be done. I won't go into how it's done, but I should say one thing, that some of the technology in this proof draws upon concepts that first came up in distributed algorithms. So Danupon was talking this morning about this interplay of techniques between different models, and I think you see a bit of that out here. Okay, so if you're good with just an existential thing, saying that you've used a small space to collect what you need, and now just existentially you can find a list coloring, then you can go home at this point. But of course, if you want this algorithm to be at all practical, then you need to show a polynomial time algorithm to find that list coloring, which they do. Okay, and it is a non-trivial algorithm. You have to compute some matchings and so on. So it's not completely obvious what to do. Okay. So that is my summary of this great ACK result, and I will refer to this as the ACK result or ACK theorem or whatever. So the final thing that you get is a randomized algorithm to compute a delta plus 1 coloring using n times polylog n space, right? And anything of the form n times polylog n will be denoted by this tilde here to hide the polylog factors, and this is commonly referred to as semi-streaming in the literature. Okay, any questions at this point about this? This is kind of the intro material, the prelude.
If we are happy to slide like a bigger size, instead of delta plus 1, we allow like this like a simpler.
Yes, indeed. In fact, if you, I briefly mentioned this result. I didn't tell you. Well, I guess I did tell you what the result is, but the algorithm behind this is especially simple. Yeah, that's right. Yes. Oh, very good question, because indeed this is one of the questions that we could ask. Yeah, all right. So fine. Without further ado, let's dive into the roadmap for the main part of the talk. So as I said in the title, this is going to be vignettes, and I'll have 3 vignettes to present to you. If time permits, there may be a bonus vignette. We'll see. But the 3 things that I want to present for sure are first of all, we know from the intro slides that we can color any graph with kappa plus 1 colors, right? This kappa being this degeneracy parameter. So is there a similar algorithm, or is there an algorithm, just as there was the ACK algorithm to get to delta plus 1? And it turns out the answer is no. In fact, the answer is a pretty strong no. This doesn't have a sublinear algorithm at all. Okay? You can prove a little more that you cannot do better than kappa plus square root kappa, number of colors. So up to an excess of square root kappa doesn't make the problem any easier. Okay, right. Next vignette is this question that was just asked. Can you make the algorithm deterministic? And here too the answer is no, or at least the ACK algorithm was a 1-pass algorithm. If you must have a 1-pass algorithm, it cannot be deterministic. So we can prove that a semi-streaming space algorithm, which is deterministic in 1-pass, must use at least delta squared colors. Right? And in fact, this theorem here proves a bit more. It shows that this lower bound generalizes to robust streaming algorithms. If you don't know what the word robust means, don't worry, it will get defined at the appropriate time. For now, all you need to know is that robustness is a weaker requirement than determinism. Okay? Now, there is a different result concurrent to ours, which shows that if, in fact, you do require the stronger determinism requirement, then not only do you need delta squared colors, in fact, you need a super polynomial in delta number of colors. Okay? By the way, this is a tricky thing here. I mean, what does super polynomial even mean? Because I mean, n is the maximum number of colors you would ever need. So for this result to be meaningful, you have to think of delta as being more than logarithmic but less than polynomial. Right? Okay. Anyway. All right. So no deterministic algorithm, right? Third vignette is going to say, there is a deterministic algorithm. We can de-randomize it, but you have to use more passes, of course, in light of the previous theorem. So we're going to show how we can do this in about log delta passes, right? And this algorithm is definitely inspired by some algorithms recently developed in the congest model. I could have chosen one of several references here. Maybe the most immediately relevant one is the one by Ghaffari and Kuhn. And this vignette is the one that I want to spend some time on, so maybe it should be a short story rather than a vignette. The other 2 I'll just be quick. Okay. And I'll present them in this order, hence this list is not numbered in the obvious way. Yeah.
I have a question, so these negative variables, but can you prove that in 1 pass you can say delta to the power delta to the power delta colors if you take, can do deterministic?
1 pass with a lot of colors. I haven't given this thought. I don't want to throw out a conjecture on the fly and get it wrong, but yeah.
Anything which is just functional.
Yeah, no, I understand what you're saying. Of course, I mean, it's a tricky thing. So there's not that many values of delta for which such a result would even be interesting, right? Because if delta is as small as log n, then your semi-streaming space, you can just store the whole graph. And then, of course, you can color with the optimum number of colors. So in order for a crazy function of delta like that to be interesting, it's a very limited range of delta in which it would be. So, I don't know. But it's true, I haven't given this active, so yeah.
So is the number of passes that you're mentioning log of delta, is that right, or can you actually lower it down to say log delta?
That's a very good question too, and that is an open. I will end with an open question related to every vignette, and that is the open question related to this one. Yes.
Okay,
yes.
Second question.
Yeah.
By robust, do you actually mean pseudo-deterministic algorithms, or do you mean something else?
No, it is something else. I will define it when the time comes.
Okay, so any results in the pseudo-determinism setting?
So
relax determinism.
So okay, so since you know about pseudo-determinism, robust is an even weaker condition. Yeah. So determinism is the strongest thing. Pseudo-determinism weaker than that, and robust is weaker than that.
Okay.
Yeah. Okay. All right. So I will talk something about communication complexity if I have time. We'll see. Yeah. Okay. Let's start with vignette 1. This will be relatively quick, but I wanted to show you a cool reduction. By the way, in each case, and I've cited the relevant publications here, And in each case, I'm only presenting one result in these papers, and it's not even necessarily the main result. But the one that I'm going to spend time on is arguably that is the main result. Okay. All right. Okay, so just to remind you about the index problem, Jai Kumar started things off very nicely by giving a gentle introduction to all this. In the index communication problem, Alice has a string of n bits, and Bob has a number between 1 and n. The goal is to find the kth bit of the data string x, right, with a message going from Alice to Bob, sort of going in the wrong direction. Okay, the well-known result here is that any one-way randomized communication protocol like this will require Alice to essentially communicate her entire string to Bob. Okay, so up to constant factors, she can do nothing non-trivial. Now this is used in a plethora of lower bounds, including this lower bound. So reducing from index, we will use n equals p squared, where p is this number over here. You'll set up a graph with 5 blocks of vertices. Each block will have p vertices in it. Okay, and I call these blocks A, B, and A prime, B prime. Okay, the possible edges in this graph are kind of going to be between A and B. So notice that there are p squared possible edges between A and B. So I can encode a a p squared bit string, an n bit string, in the space of edges between A and B, right? So an edge is present if the corresponding bit is a 1 in the data string x. Okay. So on Alice's side, she's going to encode her string x by placing the appropriate subset of edges, but she's also going to place kind of the complement of that same subset down here, right? So she's going to encode 1 minus x, the complement of x, down here. All right. Bob is going to throw in a clique, make C be a clique, and then he has a specific index. So it's an index into this p squared bit string, right? So an index corresponds to a pair of indices between 1 and k, really, right? So an index is a tuple, right? I comma j. Okay, so an index is a pair of vertices, one here, and then their mirror images also over here. So there's a vertex, say AI bj, not a vertex, but a pair of vertices AI bj over here, and their mirror images AI prime bj prime. So Bob is going to add all the edges, besides the edges in C, all the edges between AI bj, AI prime, and bj prime, except for the edge AI bj and the edge AI prime bj prime, right? So the two things shown in dashed red are not added by Bob. Everything else is added. Okay, so now you have to do a little bit of case analysis to check that this gives you a degeneracy of p plus 2. It's better to just believe me on this and not try to verify it right now. Okay, so this means that a kappa plus 1 coloring will need to use p plus 3 colors. Okay, now look at these p plus 4 vertices. Okay, so there's p vertices here, and then there's these 4 vertices, I, J, AI, BJ, AI prime, BJ prime, right? We're using only p plus 3 colors. So pigeonhole tells you 2 of these vertices must have the same color. Okay, and which 2 vertices? Whichever 2 vertices get the same color reveals whether or not the data bit xij is 0 or 1. So you've solved index, basically. Okay, so this is the nature of the reduction. So even if you can't completely agree with my logic because it's a bit fast, just this gives you a sense of the shape of this reduction. Yeah.
What's the size of the clique that you're using?
P. Everything is P. All 5 blocks are P vertices. Okay. Okay, so good. So you can't do k plus 1, kappa plus 1 coloring in any sublinear space. Okay, I did say something about kappa plus root kappa, and I'm not showing you how that's done. That's done by kind of doing a graph product construction on this graph. Okay, so moving on to my second vignette, which, as I said, is the one I'm going to spend most time on. So we expand it into a bit of a short story. Let's talk about how to de-randomize the ACK algorithm. Actually, the algorithm we have will not look like ACK's algorithm anymore, but it is a deterministic algorithm that does the same thing, okay, in a few passes.
What is the maximum degree?
The maximum degree is, I think, p plus 4, no? There's p here, and yeah, it's these p vertices are connected to all 4 of these.
Kappa and they're very, very close.
In this example there, yes, that's right. Of course, as the star graph shows, they need not be.
No, I'm just wondering if like a 1 plus epsilon kappa is easy.
Yes, 1 plus epsilon times kappa is easy. In fact, same paper, the paper with Bera and Ghosh, we show kappa plus kappa over log n. So kappa plus little of kappa is possible.
Come to maximum degree with 2p because 4 is connected to all of C and might also be connected to all of P.
Oh, sure. Okay, yes, thank you. Right, because of the blue edges, right, there may be many more. Okay, right, so let's look at our first substantial algorithm. Actually, the only substantial algorithm that I'll present in the talk. Okay, so there's going to be a form of palette sparsification going on here, but of course nothing can be done in a randomized fashion, so it will be done in a very systematic fashion. So there'll be a notion of starting with a color palette, which initially is all of delta plus 1, and then we will slowly thin it down, reduce it for every vertex in some systematic way. Okay, somewhere in the middle of this algorithm, we would have computed a color for some number of vertices and a palette, which may not be the full palette, for other vertices. Right? So this structure we'll refer to as a partially committed coloring, PCC, and what it is the following. So every vertex is going to get a color, or it's either going to get a color or it will be uncolored. So U will be the set of uncolored vertices. But if it's uncolored, there will be an associated palette from which its color will eventually be chosen. Okay, now these palettes aren't completely arbitrary. They must satisfy a very stringent condition. Given any two vertices, adjacent or not, given any two vertices, either their palettes are the same or they're disjoint. Okay, so as you reduce from the big palette to smaller palettes, you have to keep this condition, and so you have to do things in a very systematic way. Okay, now given such a PCC, I'm going to define a concept called the slack of a vertex, and this concept will, if you're used to some of the distributed algorithms for coloring, they also use a concept called slack. It is not the same definition. It's similar but not the same. This definition has been altered just in the right way to make it possible to do a streaming algorithm. Anyway, so our slack is defined as follows. So the slack of, the way to read this is slack of x with respect to t. Slack of vertex x with respect to a palette t. It's defined as the number of colors in the palette. So over here there's AT minus the number of neighbors of x that have a color in this palette, right? So in this case, say 67, the difference of 13, so that's the slack in this case, right? So notice that the neighbors of x that have colors not in T play no role, and of course the uncolored neighbors of x don't play any role either. So it only matters which neighbors of x have colors in T. You will note that this quantity is a lower bound on the number of colors in this palette that haven't been used in the neighborhood and are therefore available to be used for x, right? So this quantity over here is the number of free colors for the vertex x, right? And why is this a lower bound and not an equality? It's because in the definition of slack, if the same color appears multiple times in this neighborhood, we're actually going to subtract it that many times, right? So over here this pink color appears 2 times, so we're actually going to subtract 2. Although we need only subtract 1 because it only kills off 1 color for x, right? So hence this is an inequality. You will also note that slack is always a non-negative quantity. Do you see why? If you don't see why, it's because you haven't noticed this subtle dot on top of the minus. Okay, so this is not really a minus. It's what is called monus. Okay, it's, if you understand what I mean, right? So if this turns out to be negative, just clip it to 0, right? Okay. So yes, so slack is going to be non-negative. In fact, it's also going to be greater than or equal to 1 because of how the algorithm will be designed. So there will always be a slack of 1. Okay, so now I'm going to start to outline the algorithm. So the algorithm will proceed in epochs. Each epoch is going to shrink the set of uncolored vertices by some constant factor, right? And it's going to do this in stages. So the algorithm is in epochs. Each epoch is made of stages. Each stage of the epoch is going to slightly refine the current PCC by partitioning every palette at every vertex. Right? So every px is going to get partitioned, and then I guess we zoom into one of the parts of this partition. That's our new palette. Okay, so whatever this refinement procedure is going to maintain this invariant, as I said. That there will always be at least one slack. So these px's are shrinking as in successive stages, and at the end of the epoch, each palette size will be 1, so it will be a singleton. Okay. At this point, the constraint that you must color a vertex from its palette tells us that you must give vertex x whichever color is in px, right? So how about that's how we complete the coloring. Okay, so yeah, it's a good idea, but no, that's not what we do. If you were to do that, you'd get a lot of monochromatic edges. However, we can prove, and this is the main technical thing to prove, that the conflict graph, which consists of all the monochromatic edges, will have a large enough independent set. So then instead of committing to this color for every vertex, we only commit to it on that independent set. Okay, so then there's no monochromatic edge created, and we have shrunk the uncolored set by enough. So that's the end of the epoch, and then rinse repeat. Okay, so this is just the same thing but in short pseudocode. Right? So we start this way, we'll proceed in epochs until we have this number of vertices, this number of uncolored vertices left. We'll run a number of stages inside each epoch. It turns out that there will be 3 passes required for each stage. You can start to see that if we begin with n uncolored vertices and stop at n over delta, then we'll need log delta such epochs. Okay? So you start to see where the log delta passes comes from. Okay? What's special about this number n over delta? Well, this n over delta is small enough that once you've shrunk the uncolored vertices that much, you have space to just collect everything that you need to collect in one last pass and finish the job. Okay, so that's the general shape of the algorithm. So what remains? Main thing to talk about is what is going on over here with this refinement. Right? What happens in a stage? Okay, so let's look at our example again. It's best to understand this by picture rather than look at formulas. So we're going to subdivide this palette in some systematic way into k parts. In this example, I'm going to use k equals 4. So we subdivide the palette into 4 parts. Okay, so there's going to be 20 colors in each part. And now imagine the following random procedure that we restrict for each vertex the palette px to one of the parts, so px comma j, right? And we restrict it as follows. So we will randomly choose to either go to T1 or T2 or T3 or T4, but not with equal probability, with probability proportional to the slack. Okay, so the slack that we would have if we had chosen T1, if we had chosen T2, etc. So in this case, as you will see, if we had chosen T1, then there's 20 colors in here, and say 17 of these neighbors happen to have colors in T1. So the slack would be 20 minus 17, or 3. In this case, it would be 20 minus 7, which is 13. In this case, it would be 20 minus 28, which is 0. Yep. And in this fourth case, it would be 20 minus 15, which is 5. Okay, right. So you understand what's going on. So this gives us a new palette collection. So palette collection is one for every vertex. And that's basically the end of our stage. Okay? Now what I've described to you here is a random procedure. Of course, we're trying to design a deterministic algorithm. So we have to make deterministic choices so that it's as good as these random choices. Now in order to tell you how to do that, I have to tell you what is good about these choices, right? So to define goodness, I'm going to define this quantity called the potential of a PCC. You can just stare at the definition. Once you have the slacks, it's saying sum over all edges among the uncolored vertices where the palettes are the same, right? So you sum over all edges where the palettes are the same, and you sum this quantity, 1 over slack of x plus 1 over slack of y. Okay, so with a little bit of algebra, which I won't show you, you can prove that were you to give each vertex a random color from its palette, like a uniform random color from its palette, like available one, something that's not already used in the neighborhood, this will create at most half of this potential number of monochromatic edges. So the potential is a measure of how bad it would be to continue the coloring from this PCC, right? So if the potential is small, then we like it because it won't create too many monochromatic edges. So the goal of the refinement will be to keep this potential small, right? Now another thing you can check by doing some algebra is that if you choose the subpalettes according to this random procedure, then the expected potential of the resulting PCC is going to be less than or equal to the current potential, right? See what I'm saying? So I have a certain random procedure for shrinking each palette so that the new potential is less than or equal to the old potential. So then the probabilistic method tells me that there must exist a choice of j for each x so that the same phenomenon happens, right? New potential is less than or equal to the old. Okay, so that's what we're going to do in the algorithm. We're going to find a set of choices so that the new potential is less than or equal to the old. So now what remains to do is to say how to do this algorithmically, okay, and that too in a streaming algorithm. One thing that will definitely not work is try out every possible assignment. There's too many of them, right? Okay. All right, so suppose you did this. So we'll return to the algorithmic challenge afterwards. Let's finish off this analysis for why this shrinks the number of uncolored vertices. So suppose you could do this, always reducing the potential. Then how to analyze what this does for the algorithm. So to analyze this, I'll define this notion of conflict graph. This is kind of the natural thing that you would define anyway. So the conflict graph says it's on the uncolored vertices, and the edges are those edges of the original graph for which the two palettes are the same, right? Notice that these are the only situations where I might possibly assign the same color to x and y, because you might remember that we had the condition on palettes that they're either the same or they're disjoint. Okay? So if they're not the same, then there's no danger of giving them the same color. All right. Good. So now, do a little more algebra here. Here's the definition of potential. If you just, I guess this is combinatorics rather than algebra, but you just count how many times this term appears, and you'll find that for each vertex x, it appears exactly as many times as its degree in this conflict graph. Okay? So you have this equation over here. Now this equation is going to be useful to understand what's going on with these potentials. So in the initial PCC, what happens initially at the start of an epoch? So at the start of an epoch, we haven't shrunk the palettes at all. Every palette is delta plus 1. Okay? So what is the slack of a vertex in this case? Well, it's delta plus 1 minus however many neighbors of x are already colored. Right? Anytime a neighbor of x is colored, it's definitely using a color from this palette because this is the full palette. Right? Okay, so this black term is the slack of x. The degree of x is the number of neighbors that are uncolored, right? So that's just part of this conflict graph, right? All the palettes are the same initially because everything is equal to delta plus 1. So this condition is always true. So this is simply the number of neighbors. Okay. Okay. So if you combine neighbors of x not in U and neighbors of x in U, then the total is just the number of neighbors of x, which is the degree of x. Okay. So this thing is at least 1. Okay. So why did I do this line of analysis? So here I'm looking at this fraction over here, and I'm doing denominator minus numerator, right? So denominator minus numerator is at least 1. Therefore, this fraction is a fraction less than 1. Yeah? So in this sum, every fraction is less than 1, and therefore the sum is upper bounded by size of u. Okay, good. So what I've shown is that the initial PCC has a potential of at most u. Now think of the final PCC. At the end of the epoch, the palettes are all of size 1, and I maintain this invariant that there's always slack. Okay, so that means the slack is exactly 1. The slack is at most the palette size, and it's also at least 1, therefore it has to be equal to 1. Okay, so if all the slacks are 1, then the final potential is just the sum of the degrees in the conflict graph, so it's twice the number of edges in the conflict graph. Okay. So to summarize, I know what the initial PCC's potential is and what the final potential is. Alright, so let's put these together. So the initial potential is at most size of u, the final potential is 2 times size of f. Okay. And remember that the way we did the logic of the stages, we keep reducing the potential each time. So the final potential is going to be less than or equal to the initial one. Right? So 2f is going to be less than or equal to u. Okay? All right. So this final conflict graph that we have, see, remember the edges in the conflict graph tells us what might become monochromatic. Right? So I want to argue that, okay, it's not too bad, not too many things will become monochromatic, and in fact I can find a large independent set. How do I find this large independent set? Okay, we call upon our old friend Tyrannosaurus, right? Okay, I actually some of you were here to see that character from before. So Turan's theorem tells us how much of an independent set you're guaranteed if you have this bound on the number of edges, and in this case it gives you u over 2. Okay, good. So this means that we have shrunk the number of uncolored vertices by a factor of half, and then you know how the algorithm works from here on. Okay, there is this algorithmic challenge of how to make those choices, right? We have to choose a part for each vertex. Now, you could say that one way to do it is to choose the j values to minimize the new potential, right? That would be the best choice. Your goal is to get new potential less than or equal to the old one. But to actually minimize, you have to compute too much, right? So it is getting a bit late in the talk, so I will not try to make you think through a calculation. But just trust me that you have way too many sets of values to keep track of, and you can't do this. So instead, what we do is revisit the argument by which we prove the existence of a set of choices. We use the probabilistic methods, right? We said if you make independent random choices for each vertex according to a certain distribution, then the potential, expected potential is less than or equal to the old one. So you say instead of independent choices, how about you make slightly correlated choices? So use a pseudo-random choice, meaning use a hash function computed on each vertex to make a pseudo-random choice of partition number. part number. Okay, you will lose independence, but you can run through a similar calculation and show that the new potential is still kind of less than or equal to the old potential. I'm saying kind of because there's a little bit of a fudging going on there, but yeah, you get more or less the same behavior, right? Okay, but why would this help? The reason this would help is because your hash function can come from a much smaller hash family. So now instead of trying all possible ways of choosing a part for each vertex, you only have to try all possible hash functions. That's a much smaller number, and you can do this. Okay. Good. This idea is used in several algorithms. So those of you who are seasoned algorithm designers might recognize this idea from something else that you've done. Okay, so as I said, you will lose something slightly. The potential is no longer guaranteed to decrease. It can grow, but you can bound how much it grows by. And here you'll have to trust me on this, that you can show that the final potential will be at most twice the initial potential after all this. So instead of shrinking u by half, it's going to shrink it to 2/3 of what it used to be. Okay, still good enough. So the final algorithm then looks something like this. This is basically the same outline as before, but with a little more detail. And I think that in the interest of time, and considering what else I want to talk about, I won't go into the details of what exactly we do with all the hash functions, which is what is not shown in here. All right? But maybe take half a minute to stare at this and let me know if you have a question that I can answer. If I can answer it quickly, I will. Yeah, start with all vertices uncolored. We have epochs. Epochs have stages. I've shown you kind of what to do in a stage, and okay, fine. What's missing over here is that you go over all possible hash functions. You compute what would be the result of what would be the new potential had you used this particular hash function, and then you choose the best hash function. Okay, in some way. All right. There's some extra stuff going on here, such as using 2 passes and so on and so forth, because the hash family is of size about n squared rather than n, so you have to do it in 2 passes. Okay, but the upshot of all this is at the end of it all, we'll get a delta plus 1 coloring algorithm which uses semi-streaming space and slightly over log delta passes. So here I've laid out exactly how much it is. You can probably see where the log delta is coming from, right? Because you're shrinking by a constant factor until you get to this size. The other log delta is coming from the fact that you have several stages and you kind of have to do the math to figure out how many passes there are. Now, yeah, okay, so let me move on to my third and final planned vignette. Okay, I want to show you that we could not have done all of this in one pass. Okay? So this used many passes. And like I said, there's now 2 different ways to prove it, one of which gives you a stronger result in terms of number of colors that you would need to use with a one-pass algorithm. But the other one is stronger in the sense of doing more than just deterministic. Right? And this gives me the opportunity to present this model of robust streaming algorithms, which I trust not too many of you know about, but I think it's a nice little thing to think about. And I've been working in this space for a while now, and just wanted to make you aware of this model. Okay, so what is going on with a robust streaming algorithm is that you are deploying a streaming algorithm in the real world, and maybe an analyst in the real world runs your streaming algorithm, and based on the analysis, creates more instances for your algorithm to run. Okay, so that's rather abstract, but here's a concrete example. Maybe you have a movie recommendation system that analyzes viewership trends to make movie recommendations. But of course, once a recommendation system makes recommendations, it affects the viewership trends, right? So future results may depend on past outputs. Now, once this happens, a lot of the analysis that we do in streaming algorithms has to be thrown out because it cannot handle that the input may depend on the randomness being used by the algorithm. Right? Now, if you take a conservative view of things, you will say that the world is unpredictable. We don't know exactly in what way the future inputs will be affected by the past runs of the algorithm. So we'll just assume that there's an adversary out there who's out to get you, who's giving you inputs for your streaming algorithm that depend on all your past outputs. Okay. So now just let's define the model by picture here. So we'll now view a streaming algorithm as a game between an algorithm, which has to run in low space, and an adversary who is computationally unbounded, and the adversary feeds in the tokens that constitute the algorithm's input stream, and each token possibly depends on all previously seen results from the algorithm, right? Yeah. Our goal is that over the lifetime of this algorithm, we must achieve an error of at most delta. Oh, just an alternate picture of the same thing. Now, I'm not actually going to show you any robust algorithm today. I'm just going to show you a lower bound, though there are algorithms in that paper as well. So let me tell you quickly how a lower bound might get proven. So once again, we use communication complexity, but the shape of the communication problem is a bit different, right? So instead of Alice and Bob both having inputs and trying to compute something, the kind of communication problem that's useful here is that Alice gets a certain input, which you can think of as a prefix of a certain stream. She then sends over a sketch to Bob, and now Bob does a lot of work at his end. So he queries the algorithm to extract some information about Alice's input. Right? This is just a general. This is true in general, right? So if Alice sends you some information, which is the state of a streaming algorithm, and then you produce some outputs from the streaming algorithm, then you've learned something about Alice's input. Okay, so whatever Bob has learned, he just spits out. Okay, so he exfiltrates this information. But now Bob continues the algorithm by feeding fresh tokens into the streaming algorithm, right? And then performs another query and exfiltrates some more information and so on and so forth. So after doing all this, Bob has extracted some large amount of information y about Alice's input x. Okay, this is going to be the shape of the communication protocol. So now let's look at a concrete problem in this model. So the concrete problem will be what I call subset avoidance. And if you go away from this talk having forgotten all else about what I'm saying about robust, I hope you remember this problem. It's a clean little combinatorial problem, and it seems that it's the right thing to use for reductions. There's a universe, M. Alice has a set of size A as her input, which she then describes to Bob in this one round. Bob's goal is to produce a large set B of size B that is completely avoiding Alice's set, i.e. it's disjoint from Alice's set. Okay, so this is a clean communication problem. We can analyze it. We have a lower bound for how much communication this requires, and the answer is A times B over M. Right? I mean, this is not supposed to be immediate. It's also not too hard to prove, but anyway, I'm just telling you this is what it is. It's A times B over M. This answer is basically correct. You can prove a matching upper bound, more or less. In fact, the matching upper bound is good for a deterministic algorithm as well, etc. Right? You can also prove a direct sum version of this result, which says that in the direct sum version, there's just R copies of the original problem. So Alice gets R sets instead of one single set, and Bob has to produce R sets. Each set has to be disjoint from the corresponding set of Alice. Okay, and so you can show that the complexity of this problem is R times the complexity of the original problem. Right? And this is the result that one needs to prove the graph coloring streaming result. Okay. So even if I lose you on the next slide, I hope you remember this subset avoidance problem. It's a nice clean problem that you can use for reductions to other things. Okay, so I will try with a very rough picture to tell you how one reduces this to coloring, right? So suppose you want to solve an instance of subset avoidance, and you have a robust streaming algorithm for doing k coloring. And I'm just going to look at this parameter regime where k is order delta. Okay? So not delta plus 1, but big O of delta. Okay, so here's Alice's set. She's going to embed her set into the edge space of some graph that has about square root of this number of vertices. Make sense? So if A lives in a universe of size m, and I look at a graph with square root m vertices, then I have enough possible edges to capture this set, right? Okay, so Alice's set turns into some graph on these many vertices. Now she simulates the robust coloring algorithm and sends Bob whatever that does. So what Bob is able to do is extract a coloring, right? Extract a good coloring with about big O of delta colors. Okay, so this coloring basically splits the vertices into k color classes. Each color class is of course an independent set. Now inside each color class, Bob goes ahead and places a maximum matching, right? So just pairs up the vertices in each color class. So Bob is now going to add all of these matching edges into the graph and go back here. So now we have a slightly larger graph, by adding a matching, we ensure that every degree increases by only 1. So it is important, of course, that this graph has to have max degree delta. Otherwise, the algorithm is no good, right? So it only works on max degree delta. Okay. So by adding a matching, we ensure that it is legit to run this algorithm again. And now we have new color classes, right? Notice that these new color classes are guaranteed to extract a fresh set of non-edges. So over here, these matchings that Bob is adding are guaranteed to be non-edges in the original graph. Okay? That's the definition of a color class. These are all independent. So therefore, when you add a matching here, you're adding non-edges in the original graph. Okay. So by repeating this process enough times, Bob gets lots of different matchings, all of which are non-edges in the original graph. In other words, he finds a big subset that is disjoint from Alice's set. In other words, he solves the avoid problem. Okay, so then you apply the avoid lower bound, do the math, and you ultimately get that the streaming algorithm must use space n squared. Right? This is not quite what I promised you, right? I promised you that a semi-streaming algorithm needs delta squared colors. What I proved is something else. But to get what I promised you, you have to do a similar reduction, but from this more complicated direct sum version of the avoid problem. So just trust me on this, that once you do that, you can play with the parameters and then you can get what I promised. Okay, so there end my planned vignettes. So I should ask the session chair how much I have in terms of time. 5. Okay, at least 5. In which case I will say a little something about communication complexity. It definitely won't take more than 5. Okay. Bonus vignette. Communication complexity. Good. We've seen some variants of this problem before, except it wasn't coloring. We were doing other things on graphs, right? So various speakers have already talked about solving graph problems in a communication setting. Now you have Alice and Bob. They can go back and forth. So it's no longer a one-way thing. The edges of your graph are partitioned in some arbitrary manner between Alice and Bob, and you want to try and compute a delta plus 1 coloring. How much do they need to communicate to do this? Okay? All right. So let's start by making simple observation. You could simulate the greedy coloring algorithm. So consider the vertices one at a time in any arbitrary order. When you consider a vertex, Alice and Bob have to communicate to decide what color to give this vertex. Okay? How will they decide? So they need to know what colors are available for this vertex. So from Alice's point of view, she knows a certain set of neighbors of X, and then Bob knows a certain other set of neighbors of X. Okay? According to Alice's view, the colors in F sub A are free, and according to Bob's view, the colors in F sub B are free. And of course, the color chosen has to be free for both Alice and Bob, so you want to find an element in the intersection, FA intersect FB. Okay? That's the goal at each vertex. Okay, now if you're used to communication complexity, then anytime you see an instance of must find an intersection between two sets, alarm bell should go off saying, oh, that set disjoint is a hard problem, right? Except it's not. There's a very strong promise that we know. This degree guarantee and the fact that you have a palette that's one larger than the degree is going to guarantee to us that FA and FB add up to more than the palette available to you, right? So in other words, you have to find an intersection between two sets whose sizes are large enough that by pigeonhole principle, the intersection is guaranteed to exist. Okay, this is a much easier problem. You can binary search for an intersection. So that will take log delta rounds and log squared delta bits of communication, right? Does this problem remind anybody of anything they've seen before? And can anybody imagine a better protocol than binary search? Is Jaikumar here? That would be the right person. I don't see him. Oh, Jaikumar is here. I bet you know what to do. If you think you don't know, then once I reveal the next thing, you will realize you did know. Okay, anyway. There is a way to get a better protocol, but it's not explicit. I can't tell you what the moves of the protocol are. So I will not actually try to describe this, but I will point you to two classic references in complexity theory. One by Valiant, who gave a monotone formula for the majority function. Okay, majority has polynomial size monotone formulas. That's the result. A different classic result is a result of Karchmer and Wigderson that connects formula depth with communication complexity. So if you know these two things and you throw these, use these hammers, then you can reduce the communication to log delta. Okay, now Jaikumar is nodding and he knows what to do exactly. All right. So for the rest of you, I guess I can tell you offline, or you can puzzle it out. Okay. All right, overall we have a deterministic algorithm that uses n log delta communication and runs in n log delta rounds. That's what we got out of the greedy algorithm. Now if you want to use fewer rounds, you could simulate instead one of these streaming algorithms. You could simulate the ACK algorithm that would give you a randomized one round protocol, but the communication would be n times log cube n. Okay, so it's a bit more expensive in terms of bits of communication. Or you could use the deterministic algorithm that I presented earlier, and that would give you something like n log cube n, log n communication, similar amount of communication, and in more rounds, but now it's deterministic. Okay. Okay, so what remains open then? So could you maybe get down to n log delta communication, but in a small number of rounds, right? Is it possible to get the best of both worlds? So you do see that n log delta is the best possible communication, right? There's n vertices. Each vertex has a color between 1 and delta. It's log delta bits to write down the color of each vertex. All right? Okay, so I've got many of you nodding. All right. No, you can do better than n log delta. All right. So what happens? How is this even possible? I thought I just convinced you that every vertex needs to write down its color. So no, every vertex does not need to write down its color. You can do the following trick. So you can prove that, okay, so here this set Cn delta is a set of possible colorings using delta plus 1 colors, right? Right? So this delta plus 1 to the n is just the set of all possible colorings that you might give an n vertex graph. There's a suitable set Cn delta whose cardinality is not too big, and it has the property that any delta degree bounded graph will have a proper coloring from this restricted set Cn delta. So you can name a coloring for your whole graph by just indexing into this set Cn delta, right? So that actually requires less. That requires only order n bits. So at least existentially, it's possible, it's conceivable that there is a communication protocol that only communicates order n and not n log delta, right? But find it. Can you find such a protocol? So this has been done. So this is recent work of Flynn and Mitchell. They showed that you can get order n communication, but they do use a lot of rounds. So it's n log delta rounds. So then new question is, can you reduce the number of rounds down to something like what we had shown with the streaming algorithms? And this too has been done now. So latest in the QuadC this year, this team from Singapore showed that you can get order n communication in something like our number of rounds, log delta, log n, right? This uses a number of ideas from the distributed computing world, like local and congest model algorithms. Okay. Because I won't say more about that. Good. So I just wanted to make a plug for these two very nice communication results. Okay, let me wrap things up by acknowledging my collaborators in the work that I presented. Suman Bera, Prantar Ghosh, Manuel Stockel, all former students of mine, and Saper Asadi, who sadly could not be here at this workshop, but would obviously have been one of the stalwarts. And thank you to NSF for funding me. As promised, I will end with one open problem related to each vignette. So I talked about degeneracy coloring in the beginning. Is it possible to get down to kappa plus root kappa colors in semi-streaming? We don't know how to do this, right? This is the lower bound stops here. So the lower bound says you can't do better than this, but it's open that you could do these many colors. On the robust side, I didn't present any algorithms to you.
Hello everybody. Is it on? I don't know if it's on. Is it on? Okay. Hello everybody. Welcome to the last talk of this day. It's my pleasure to welcome Professor Saket Saurabh. He's a faculty at IISc and adjunct faculty at Brigham. He's a prolific researcher, done some fundamental work on parameterized complexity and exact algorithms. And as a result, he has won numerous awards and fellowship. And I'd like to just mention some sort of Bhatnagar Prize and the ACM India Young Fellow Researcher Prize. And so let's just listen to him and what he has to say about his new algorithm, new parameterized algorithm for hedge cut.
Thanks a lot. So you already have heard about hedge cut in the morning when Devamala was talking about it. So I will tell you a little bit about the hedge cut problem, its complexity, and what we do. And it's a joint work with Federer, Piotr, Tuka, and Daniel, and it appeared at Soda this year. So let's just get started and let's look at the problem. So basically in this problem, you can just think of a graph G whose edges are partitioned into groups called hedges, and you have to decide whether you can delete some L hedges to disconnect the graph, right? So think of each hedge as like some edge bundle, and when you say, okay, I delete this hedge, it means you delete all the edges in that bundle, okay? And that's it. So this is the problem we have. So we want to test whether I will given a hedge where my edges are partitioned, each part is called a hedge, so that can I delete minimum number of hedges such that the graph becomes disconnected, okay? So this problem appears in network survivability, and this is also called global label min cut, and models failures where a set of links may go down simultaneously. So this is from where it comes from. It has also been studied in phylogenetics, and it is called minimum cut in colored graphs, okay? So for example, look at this graph. So what is global min cut? Is like minimum number of edges whose deletion disconnects J, and hedge cuts. So like imagine that all these gray edges are of single color. So every edge which are gray has its own color, but I also have this red hedges H1, H2, and this green hedge H2. Now if you notice that if you were looking for minimum number of edges which disconnect, then you at least need to disconnect 3 edges in this graph to disconnect this graph. But if you talk about hedges, I can delete this red and green hedges and I will be done with it, right? So I can disconnect my graph. So this is fairly simple question, right? Is that basically you can think of this, that you can also think that your edges are partitioned or edges are colored, and when you say I delete some hedges, it means we say I'm going to delete red hedge, I'm going to delete all the edges that have been colored red, all the edges that we are going to talk about. And why does it generalize as min cut? Well, you start with a normal graph and you assign a color to every edge gets a different color, right? Then this problem is nothing but a normal global min cut. Okay, so it does generalize the global min cut problem. Okay, what about hypergraph min cut? So in hypergraph min cut, you have the same set of questions. You have given a vertex set of H and hyper edges. So now hyper edges is not 2 vertices, but it could be 3 vertices, 4 vertices. What you do is that for every hyper edge in this graph, you look at if the hyper edge consists of A, B, C, D. Then you look at every pair of those vertices and you put an edge of the same color. So every hyper edge will correspond to a set of colors. I have used click because it's easier to think. You could also use some spanning tree on the set of vertices. So now you can show that, and you keep parallel edges. So this is how it can become. So punchline is that deleting L hyper edges in H disconnects H if and only if deleting L hedges in G disconnects G. Okay? And if you wanted to restrict to simple graph, you can subdivide every edge and be fine with it. Okay? So now you notice that this problem generalizes both hypergraph min cut and the global min cut problem. Okay? Any question? Okay. So we know that we have seen many algorithms here for global min cut, polynomial time, hypergraph min cut, still polynomial time. But what about the complexity of hedge cut for general partition of edges? We know that if hedge cut special cases are polynomial time, does it mean that this problem is also polynomial time solvable for hedge graphs? And for several years, this question was open, whether it is polynomial time solvable or NP complete. And so Ghaffari, Kargar, and Panigrahi gave a quasi-polynomial time randomized algorithm for this, which ran in time n to the power big O of log L, where L is the number of hedges that you want to delete to check whether graph becomes disconnected or not. So generally what happens, the moment you see a quasi-polynomial time algorithm, it is, you believe that maybe there's a algorithm, polynomial time algorithm just somewhere around. But few years back, Jafke, Lima, Masaryk, Pelukchuk, and Soja showed that, in fact, if you assume exponential time hypothesis, then you cannot get much better algorithm than what these people have got. So you cannot get algorithm n to the power log n by polylog n. So roughly n to the power log n kind of algorithm is, you expect such kind of algorithm unless you can design an algorithm for 3-SAT running in time 2 to the power big O of n divided by say log star n or something, right? So this is what ETH means, that if you look at a 3-SAT formula for which the best known algorithm is like some 1.3 to the power n, if you can get such nice algorithm, forget about polynomial time, even if you get such algorithm, then at least you can get an algorithm for 3-SAT that will run in some exponential amount of time, which is still beyond our knowledge, and that is what is known as exponential time hypothesis. So this is the state of affair for this problem up until now. Any question?
M and L is the M here is the L there.
M is, yes, correct. Yes?
Maybe this is a very stupid question. It's kind of saying that ETH implies polynomial not equal to polynomial.
In some sense.
So people believe both ETH and...
Depends on whom you ask. Right? So I don't think you should believe anything. Like this is not the right way of looking at any of these conjunctions, that who believes what. It is way to tell us that this is a basic problem. If you want to make progress on this, like some artificial kind of problem, then the progress on that artificial problem or your problem is somehow linked with this basic problem. So maybe we should put our effort to understand this problem better. I mean, that's another way of looking at it. Right? For example, a lot of lower bounds in polynomial time algorithms come from strong exponential time hypothesis. Right? So this is just that, I mean, it's like, why do you believe P is not equal to NP? Polynomial versus NP. It's just like, here are lots of bunch of problems. They fall together into this category. Similarly, you can also make similar kind of things with different kind of complexity assumption that you start with. So algorithmically, this is another viewpoint that we take it. Any question? Okay. And what we knew about parameterized hardness, so in the same paper, they said that, okay, I know that, can I save some L edges? Like number of edges not used in an optimal cut, right? Not edges that are used in the cut, but I say, can I cut this by avoiding small number of edges? And they show that that problem is not W1 hard, means you cannot have an algorithm with running time n minus L plus m plus n to the power big O of 1. Okay? So this is what they showed in their paper. So they got one algorithm, they showed a lower bound that it cannot have a better than quasi-polynomial time algorithm, and they also had this hardness result that if you wanted to parameterize the number of edges not used in an optimal cut, then you cannot have FPT algorithm. So m minus L is the number of edges I'm not using in my cut. But the more interesting question that at least for me was open was, what about cut size L itself, right? So now I understand that it cannot have polynomial time algorithm, but it doesn't rule out having an algorithm that is FPT in L, where L is a number of edges that I need to delete so the graph becomes disconnected. Okay? And there was some algorithm for this previously. There was an algorithm with running time n to the power 2 power L by Bling, and this Bling, Bonizoni, Dondi, Rigi, and Sikoda. And if you look at the result of Gaffney, Kargan, and Panigrahi, they give, so it's quasi-polynomial in n for fixed L, but still it is not f of L poly in n. Okay? So that was the starting point of our work. So what is our results? So let me explain to you what our results are. So first we give an algorithm running in time 2 power L m plus 1 to the power big of 1. So like it is an FPT parameterized by L. Okay. In fact, we can show that this runs in time some c power L for any c greater than or equal to 1. So 1 plus epsilon to the power L. Okay. So but before I go to this is the one result that we obtained, but how do we get it? So we first study a generalization of this problem which is called hedge k-cut. So the way you have a k-cut in graph where you want to delete minimum number of edges such that the number of component is at least k, right? So what is a global min cut? You want to delete minimum number of edges such that you have at least 2 components. And what is a k-way cut? You want to delete minimum number of edges such that you have at least k connected component. Okay? So equivalently you can ask the same question here, right? I want to delete minimum number of edges, or can I delete some L edges so that the graph has at least k connected component. Okay? So for example here, right, for k equal to 3, if I delete this h1 and h2, this like blue and
red hedges, I will get 3 connected components, right? So yeah.
Sorry, very basic question. So the hedges are given as part of the input. The
Part of the input. The labels is given to you.
The labels are given and also given how many hedges the L is given.
L is given. You are asking whether can I do it with a deletion of at most L hedges.
But they are all labeled beforehand.
Beforehand, you're given to.
So there could be another problem of you are given the budget and you
Want to label it.
Label the hedges, create your own hedges.
But then, yeah, so you have to ask rightfully, because otherwise I can put all the edges of the same color and then I say delete all. So you have to also say that you have to at least give that many hedges or something of this nature to have an interesting question. Okay? So is the K-Bay cut question clear? Okay. And what was known for this? So the way global min-cut generalizes min-cut in simple graphs and hypergraphs. Similarly, hedge K-cut also generalizes global min-cut as well as hypergraph K-cut. And for both of them, there was an algorithm formed n to the power big O of k for fixed k. So for both K-cut and hypergraph K-cut, you have an algorithm of running time n to the power big O of k using this kind of randomized contraction kind of tricks. So what we give is the following algorithm. Okay? So we give a randomized algorithm which, if you're given a hedge K-cut instance and suppose it has a hedge K-cut of size exactly equal to L, then the algorithm outputs this particular C with probability sum n to the power big O of minus k divided by order k log n plus L choose L. I will decode all these numbers in a minute. Okay? So this is a randomized algorithm. It runs in polynomial time and produces, if you had a cut of size C, then it will produce a cut of this size. Now, why do I state my result in a way? Because if you notice, it is telling me that you fix your cut, I will output that particular cut with this probability, which also implies that number of such cuts are that many. So that is why I have told like this. Okay? Okay, so what is the main algorithmic result? So if you repeat this enough number of times, then you can solve hedge k cut in this kind of running time. Order k log n plus L plus L n to the power big of k time. And how many number of optimum k cuts are there? Are of this number, k log n plus L, choose L n to the power big of k. And there was a paper by Chandrasekhar, Zhu and Yu who had showed that number of hedge k cuts in graph are n to the power k log n in 2018. So I will tell you how we can recover this result from these numbers in a minute. Okay. So here is how. So let's fix a equal to order k log n, and I want to show that then a plus L choose L is nothing but a plus L choose a, which is n to the power big of k log n. How? If the number of hedges that you need is less than some a, like some k log n, then that is like 2 power a plus L choose a is nothing but 2 power a plus L, because it is less than 2 power n. And if you do all this, you will get n to the power big of k, which is definitely less than n to the power k log L. Okay. And if L is more than a, then you can a plus L choose a is like some e into a plus N choose a to the power a, 2e to the power a, and if you substitute it, you will get n to the power big of k log L. So this algorithm at the same time also recovers the algorithm of Chandrasekhar, Zhu and Yu. So it's just simple manipulations. Okay. Now what I'm going to show to you in the next slide, the same algorithm also gives us an FPT algorithm. Okay, like same running time is also an FPT running time in a minute. Okay, why? So I substitute a plus L, choose L. Why? So if the number of hedge cut is less than say some k log n, then what it is? Then it is 2 power 2a, which is n to the power big of k, which is some 1 plus epsilon to the power L to the power n to the power big of k. Right? So now, if you did not want to get this into 1 plus epsilon, other case is what? When L is more than a, then it is 2 to the power 2L. If you forget about this, so this is like n to the power big of k, and if you did not care about 1 plus epsilon, then what is the other case? Other case is L is more than a, right? L is more than a, then a plus L choose a is less than what? 2L choose L, which is some 4 to the power L or something. So if you wanted to see just an FPT, then that's all that it comes. Because y and k is like 1, then this is the algorithm for hedge min cut in the global sense. Okay? So it's just some manipulation of running time. My purpose of showing these 2 slides was that it is the same running time, which if you manipulate, it will give you a number of min cuts as well as FPT running time. Okay? But I'll give you full algorithm in a minute, which is much simpler than this computation that I'm doing here. Okay, so if you fix k equal to 1, what does it give us? It tells us that number of upper bound was like n to the power big of log L, and now it tells us that number of cuts are size 2 power L into poly n, or 1 plus epsilon to the power L into poly. So it's basically a fine-grained upper bound on the number of hedge min cuts. Okay? Any questions? So is the result okay? I'll repeat in a minute. Okay? And what is the hardness result? The hardness result says that this n to the power big O of k is unavoidable for hedge k cut. You cannot, in fact, even for hypergraph k cut is W1 hard parameterized by both k and L. So you do not expect to remove this n to the power big O of k in the running time. Okay? So what I'm going to tell you in the remaining 30 minutes is tell you proof idea for k equal to 2. So even if you have missed something, this is the time to get up, ask question. And because this is a full 30 minutes, I would say, what do you call it? You don't need anything else, but like there's nothing new happening here, so you can understand everything that is being communicated here. I'll give you a full proof for k equal to 2. So that's my plan. Okay? So what result I'm going to prove to you? Given L and a hedge graph, if G has an optimal hedge cut of size at most L, then the algorithm outputs C with probability at least this much. So that's what I'm going to show to you. I'm going to give you an algorithm, that a randomized algorithm, that you fix your C. I'm going to output that particular C with this kind of probability. Okay, so I need some terminology. So this is my hedge graphs. What is the size of a hedge? So if you notice, like edges size is 2 means number of vertices. By size of a hedge, I mean number of vertices that is incident to that hedge, right? So V in V, there exists E in H with V in E. So that's the size of a hedge. Or basically you can think of this, you look at a subgraph on the vertex set and the edges of that hedge, delete singletons, whatever vertex is left is the size of a hedge. Or in other words, what is the size of a hedge? Look at the number of vertices that is incident to any edge in that bundle. So that's the size of a hedge. Is that okay? Okay. Okay. And I will define what I mean by contracting a hedge. That I will need. So I will show you in the next slide what I mean by contracting a hedge. So what is contraction of hedge means? So look at these blue hedges, right? There are A, B, and D. So basically, look at every connected component on a particular hedge. You contract each into a single vertex. And keep the parallel edges, remove the self-loop. So what will this become? This will become this. So I look at AB, and I contracted this. This becomes single because it's a connected component. Look at other connected component DE. I contract it, it becomes a single vertex. So it is just like a normal contraction, but now same hedge might have many, many connected components. So when you contract, you will contract each connected component of this hedge. Is that fine? So this is what it means by contraction of a hedge. Meaning, you look at the hedge graph, or look at the hedges inside this, look at each connected component of this hedge, you contract into a single vertex. Okay? So this is what I mean by contracting a hedge. Okay. So here is my basic premise. Here's a simple branching rule. What is a branching rule? Imagine that I have a hedge with lots and lots of vertices in this. Right? What happens if you contract this hedge? If you have a hedge which is adjacent to say n by 2 vertices, and you contract, how many vertices will be left after this? When you contract an edge, the number of vertices in the graph reduces by 1. But if you contract an hedge on some n by 2 vertices, what will the graph reduce by? Graph will reduce by half of the number of vertices in that. Right? So that is what I'm saying to you here, is that if I decide to contract my big hedge, number of vertices in my hedge graph reduces by good fraction if I started with good big size hedge. So what is the property? If I reduce a big size hedge, number of vertices that is left after contraction is some fraction of what was remaining before, right? So when we contract a single edge in a normal class, it reduces by exactly 1, but now hedges has many things. So if you reduce, so for example, why half? Because if all these hedges were in a single component, then it will reduce by exactly that many. Worst case is when every hedge is like n by 2 component, or they will contract. So this is why number of vertices that will decrease is at least half of the hedge size. Okay. So I don't know whether this big hedge belongs to my solution or it does not belong to my solution. So if belongs to my solution, then I delete this hedge and try to find a solution of size L minus 1 on the reduced graph, right? But if I does not belong to this, then I know that I can contract this hedge and reduce the number of vertices by good fraction. So that's the heart of the branching step, right? So algorithm is fairly simple. It looks whether the hedges are big or not. If there's a big hedge, it just decides to branch, either tries to pick this edge into the solution, decreasing the opt, or it tries to contract this, decreasing the graph by a considerable fraction. Okay. Okay, so there are some simple pre-processing, like if there's a vertex whose number of hedges incident to that is like less than L, then you know that you delete all the hedges incident to this, and then you have got a hedge graph which is disconnected. It is like a simple graph. If there's a vertex of degree at most L, delete all the edges incident to that, and then you have got a disconnected graph. So similarly in the hedges, if there is some vertex, not the number of edges incident to it, but the number of hedges that are incident to it is at most L, you just delete all these hedges and then you are done. Okay? So this is where we do randomized branching, because I don't know if I get a big hedge, which of the side is okay for me. So with probability half, I decide to delete, and with probability half, I try to contract. So that's my randomized step. But what happens when my graph does not have big hedge? Then I will show to you that if you do a random contraction with some probability 1 over L, then you will not touch your hedge cut, and you will reduce the graph by a good fraction. Okay? So this is very similar to normal algorithm. If you do recursive, whatever they were telling about Kargar's algorithm, it is very similar to that. Okay? So independently, every hedge you try to contract, and you can show that you have not touched any hedge in your cut, and you have decreased the graph by a good fraction. Okay? So if I have to write the whole algorithm, this is how it looks like. If I have a big hedge, you randomly pick which side to go. Otherwise, you contract every hedge with probability 1 over L, and you recursively solve the problem either here or here. Now, let me tell you why does this algorithm succeeds. Okay? Here it is. Imagine a branch. What happens? Look at a root to leaf path. Okay? Notice that how many times in any root to leaf path L will drop? At most L times, right? And how many times this N will drop? Every time I lose fraction. So in the root to leaf path, it's not that the graph will reduce more than some order log in time. Because every time when I apply this vertex move, my graph shrinks by some fraction. So if I look at a root to leaf path, the total number of length of this path is never more than L plus big O of log n. Because L for what? For hedge cut size to decrease, and order log n for the number of vertices to decrease. Because every time if I apply either contraction, number of vertices decreases by this fraction, or I branch on a small hedge, or it's nothing, then it reduces by good fraction. So if you think through, root to leaf path is not more than some L plus big O of log n time. And that is what gives you a success of 2 to the power minus L plus big O of log n. Okay? So that's the crux of this argument, why it works. Okay? Now, notice, and this is why these algorithms are like FPT kind of running time, because 2 to the power minus L plus big O of log n, if this is a success probability, then what is the running time? 2 to the power L plus big O of log n, and what is the 2 to the power big O of log n? Is polynomial. And you can separate them out. So the most interesting thing is that even with this kind of branching, where parameter drops by 1, but in other side parameter never drops. It's just that the graph shrinks by this. If that also you're able to show that it shrinks by good fraction, then also you can win at the end. And that is the main intuition behind this, and which allows us to generalize several of the algorithms of the previous kind. Okay? Okay. So let me show you why. So this happens with probability half. So this is not a big deal. I mean, this we succeed. But why, if we have a small hedges, we succeed with constant probability to reduce the number of vertices by good fraction? So let me try to sketch argument for that. Okay? So what is a randomized contraction step? For every hedge with probability 1 over L, we decided to contract it. So I'm asking, what is the, and I'm going to show to you that with constant probability, number of vertices will be reduced by n by 40. Okay. Okay. So what is the probability that no hedge in C gets contracted? Probability that a hedge gets contracted is 1 by L. So probability that no hedge of C is contracted is 1 minus 1 by L to the power L. Okay. So which is at least 1 by 4. So now let's condition that no hedge of C is contracted. Okay. So let's call a vertex V is light if it is incident to at most L by 4 hedges in C. Okay. And what is the good vertices? Vertex V is good if it is light and its hedge degree is at least L by 2. Okay. So what it means, I will show a picture. Okay. So vertex V is light if it is incident to at most L by 4 hedges in C. Now we ask ourselves, how many vertices are light? How many vertices are light? So notice, what do you know? We are in the case when every hedge had size how much? N by 8. So total size of that hedge is NL by 8. Okay. Now, if you define what is the hedge degree of a vertex, number of hedges it is incident to, then if you sum them up, then V in V, its hedge degree is equal to cardinality of this, which is NL by 8. Now if you do some averaging argument, you can show that half the vertices are adjacent to at most L by 4 hedges in C. Okay? And when I say a vertex is good, if it is light and its hedge degree is at least L over 2. Now, okay, how many vertices are light? Every vertex has degree at least L plus 1. So every vertex is good. Right? Every vertex, so every light vertex becomes automatically good, right? So if you are light, you are definitely good because every vertex has very high degree, right? And what is good, what is light is the number of edges of your fixed hedge is at most L over 4, right? So at least L by 2 vertices are good. Okay? So again, let's see the picture. So here is my U, and here is hedges in C, and these are hedges which is not in C. So what is the definition of so hedges in C is at most L by 4, right? And hedges not in C is at least L by 4. Then these vertices are light, and why they are good? Because and every vertex which is light is also good because they are adjacent to lots and lots of hedges. Otherwise, you would have just pre-processed in the beginning. So we are in the case when we have at least half the vertices where number of hedges from your solution that they are incident to is at most L over 4, and number of hedges that is incident to them is at least L by 2. So let U be good, then U is incident to at most L by 4 hedges of C and has hedge degree at least L by 2. Right? So hence U is incident to how many hedges which is not in C? So what I'm trying to do, so I want to see that in this process, when I do every hedge, I contract uniformly. I do not want to contract I only want to contract hedges which is not in my C because I want to protect them. Okay? So no hedge incident to use contracted is what? So you are contracting every hedge with independently with probability 1 over L. So you are not contracting with 1 minus 1 by L. And how many of you don't want to contract the L by 4 hedges, which is from the C? So that's your probability. And that's like 1 over E. So if you do the maths, it is 4 over 5. So probability at least one hedge incident to you is contracted is 1 over 5. Okay, now we are more or less done. Okay, so in expectation, how many good and each vertex is hit with probability at least 1 by 5. Meaning how many vertices at least one hedge corresponding to them is contracted. So in expectation there are n by 2 vertices and with probability 1 over 5 you are contracting a hedge incident to this, that is n over 10. Okay. So now, but you want to show this with good probability, so you can show that probability that x is at least half times Ex or probability that x is at least n over 20 is 1 over 20. Like I want to say what is the probability that number of vertices who has an hedge incident to that which has been contracted is like roughly 1 over 20 because you can do this summation business. Okay, mu is like expectation, all those less than mu by 2 and all those which is greater than or equal to mu by 2 and you can just sum them up because total number of this is bounded by n. You can do this. So basically what I have shown to you is that, so if x is n by 20, means what I have shown to you that there are at least n by 2 vertices for which I have a hedge which is incident to it, which has been strong, and those are not the hedges of my C. So that is n by 20, but maybe when you contract, you merge the group of size 2, so you have decreased by some n by 40. Okay. So what we have shown to you that with probability 1 by 80, the contraction step is correct. Why? Because it does not contract any hedge in C, that is 1 minus 1 by L to the power L, which is 1 by 4. Probability that is shrunk by n by 40, avoiding condition on fifth, is 1 over 20. So it is 1 by 4 into 1 by 20 is 1 over 80. Okay? And that's the whole algorithm. Right? So algorithm is fairly simple. It just branches over what it does. It branches over big hedge, either with probability half, either it deletes it, it decreases L, or it contracts, reduces the graph. If there is no hedge, then this normal old classical idea from randomized contraction works, and it shows you that in this case I can reduce the graph by some constant fraction. Okay, any question? Or have you lost all of you people? Which is fine if I'm lost, because you needed to see some details. Okay? Okay. So how do you show this success probability? So to show success probability, you basically can show induction on L plus N. You fix FLN is 2 power minus L n to the power minus n and some g of n n to the power minus 400, some selection. And what is this belongs to? So this is to take care of this branching on the big hedge, and this is to take care of when you have only small hedge case. Okay? And what you need to show that algorithm outputs C with probability f of ln times g of n. That's all that I'm showing. Okay? And then I will be done. Okay? And now if I set it up all these things, it's fairly easy. What you did in this case, if delete if E is say else contracts, so half of fl minus 1n is nothing but f of ln. That is how I chose it. Other case is like, look at fln prime is at least fln, g of n primes is at least g of n. So if you take the product of this, this is at least this much, so you're still happy, right? So it's not rocket science. And what is small hedge with probability 1 over 80? So it is 1 over 80 times g of 39 by 40 n. And if you do this computation, these numbers are chosen in a way that this all satisfies. That's it, right? So all I want to tell you that these details are not as hairy as it looks if you set it up correctly. And something which I learned during this process is that if there are 2-3 processes happening in the probability, then you just fix up these 3 numbers and let each of them take care of different cases, and you will be perfectly fine. And if you try to muddle them together, it just gets all messy. Okay? But if you just take independent function for each steps, and then this is perfectly fine, that it works out perfectly fine for each of them. Okay? I have not tried to optimize, but this works out perfectly fine. Okay? So this is what we did. So if you do, like, we just wrote down this equation, and whatever number came, we just put it down to matter. Okay. So what are takeaway? So our hedge cut algorithm is FPT in the optimal cuts idea, but there is no evidence that the current dependence on L is optimal. So for every fixed C, we obtained these kind of algorithms. I don't know whether this can be improved to the power little of L. Maybe it is possible to do. And the evidence is 1 plus epsilon to the power L. It maybe tells us this algorithm is highly randomized. We don't know how to make deterministic. And neither of the steps. The first step where we branch on this and that, I mean, that's perfectly fine. That I can do deterministic. Either I take this or I reduce this, so that's perfectly determined. But the last step where we contract each hedge with probability 1 over L, I don't know how to make the deterministic. And that is a randomized step of this algorithm. Okay? Like, can we show that hedge k cut is FPT on some simple planar graphs parameterized by just k or even L? We don't know any of these answers. And so there was also like some betas, e-betas questions are left for hedge cut. So you can try to do them. That's open into that literature. And thank you. That's all that I want to say. Yes.
So does it, is there a way, or does it make, from your original motivation, when you said that hedges are sort of, there is this thing, if they have some connection with, let's say they have some connection with each other in the sense that the whole, when it goes down, all the edges go down together. So maybe it's is it the case where they are all forming a subgraph of some kind?
Yes, so at least the telecommunication example that I saw, they said that like these networks are connected with each other. So if one fails, the whole block fails, and this is where they get this example. So
with the least assumption of that every edge must border every other edge in the hedge.
Correct.
Is that a variant which is interesting and simpler in some ways?
Yes, I don't know.
Because that would not have that example when we contract, it will contract at least a correct subgraph. Yeah.
Right.
I mean, yeah, every edge has all the edges in the hedge have another edge which is a border, so like a subgraph of some kind. So that's not.
I don't know. I mean, I'm like, I have.
So what is the question? Is it that all the hedges are connected like subgraphs, or all the edges form a connected?
Yeah. So the hedge forms basically a connected subgraph.
So that's equivalent to hypergraph linker. That's what it is.
Correct, right. Oh, right. So if each hedge is connected, yeah, then as I tell that you can take spanning tree. So he's right. It's a high. That's much easier question. People have also studied some submodular functions of these, which are even harder than these questions. We were having just fun with this question because I saw some talk. Somewhere we saw this talk, this curious W1 hardness. So that is where. I mean, at least in my head, I don't know algorithm for which we have ETH kind of lower bound in this n to the power this. I knew some other examples like dominating set in tournaments, but I knew those problems are W1 hard. So for me, this is why it was interesting. Oh, till FPT. So that was nice. Yes. Okay. Thanks a lot. You have to give me.
Oh, yeah. Sal. Yes. Keep coming, please. Yeah, it was nice talk. I sort of missed the conversation fast, and then I realized we were mentioning. Like what happens if you end up with a large graph at the end of all the relations you've done a few number of steps and you still have like a large graph. Like what happens with the probability? That's you mentioned the tournament probability, I just missed it somehow. I will make the first.
Yeah, I
We can leave a lot of things. It was written that it's exactly like whenever we come some amount of time after 5 days exactly from that. And we entered like 2 a.m. at best. No, just check. Inform them. Yeah, but it's like inform them that you are checking out your don't ask, just tell them, oh, we'll check out if you're interested. So maybe check out on this ticket. You can keep it there. If it's not here, you can keep it here, whatever you feel.
But I think they will find the luggage.
Thank you. Account streaming algorithm.